Here's my buddy Bernie Thompson. Thank you for coming out, Bernie.
Hello. How are you all doing today? First and foremost, I want to thank each and every one of you for coming out. I know how hard it is for you to come and do training. Next, I want to thank G. I don't think you guys really appreciate what you have here. I travel all over and I train all over. No one has a TST other than you guys. There's a lot of groups, but there's nothing that has this kind of camaraderie, this kind of training, and G's expertise of putting all of this together. G is absolutely a key member in the automotive industry. And for him to really take his time like this, it's just amazing. And I would really like everyone to understand how hard he works. Can we all show him and have a standing ovation for G and TST? Thank you so much. That being said, my name is Bernie Thompson. I own Automotive Test Solutions with my business partner, Neil Peterson. During the process of designing and building equipment, I see things differently. Sometimes these things are very helpful to express to you guys what I've learned. So basically, I'm going to come here today and I'm going to try to go through some things that I've learned about the CAN network. CAN is Controller Area Network. So the first thing we want to do is, what is a communication system? So basically, a communication system is something where we communicate or we share data. Whether we're talking or whether we're using an electronic system, we need to have shared data. In communications, electronics, this is going to be a little bit different process. So I'm going to need a transmitter, a medium, and a receiver in order to accomplish this. Now, if I only had a system such as we see here with a transmitter, a medium, and a receiver, I could only send the messages one way, right? So what we really need is to have this duplicated on each side where we have a transmitter and a receiver and a transmitter. And now this will allow me to send bidirectional messages. So I can send one and I can receive one. And this is just the basics of electronic communication. A while ago when I first wrote this course, this has been a while, this was in 08 and I've revised it recently, but this is a car that I was called out to look at. The individual has no dash. His dash is out, and I'm using his scan tool. So this is the shop scan tool where I'm at. Do you see how all the dash is dead? We plug this scan tool into the bus system, and now the whole bus is down. Now, he didn't realize that the scan tool is taking the bus down. He's trying to figure out why the check engine light is on, because the check engine light came on. The vehicle was delivered for him to look at it. He took his scan tool, he plugs his scan tool in it, and now the car won't run and it won't do anything. And so he's freaking out, so he calls me, and in my business, I design diagnostic equipment. But in order to prove this tooling out, you have to go out and work on cars. So I am a mobile technician, and I go out multiple times a week, and I do 8 to 10 cars a day. I do a lot of the stuff for communications because people get confused on it. I'm going to try to deconfuse this today. So that's how I'm here, just so you understand that I have a mobile service. So this scan tool is taking down the bus. Here's the scope that's connected to the data, and that's the wiring that transmits this data. And we can see that I've got pulses, right? So that would be okay. That isn't okay. Do you see how the bottom voltage is at 3.6? It's elevated because I have a ground problem within the circuit. Always remember, the elevated voltages show that resistance is there, right? You got to have resistance in order for voltage to be there. So if I have an elevated voltage, this is some type of a resistance problem as a general rule. But I want to show you something when I unplug that scan tool. Do you see the difference? Well, if you don't go to ground, the system can't operate properly because the threshold is programmed. In other words, when you do a voltage or you're programming something, you program and you tell it you're looking for this edge, a rising edge, at a voltage threshold. You know how you set a trigger up on a scope? And you set the trigger, so you say it's a rising or a falling edge, and you say a value. Well, when you program, you've got to do the exact same thing, guys. The computer won't do anything until it's told exactly what to do. You're telling it to target a voltage on an edge, and whether it's going up or falling, and I start a clock. And an internal clock is going to run, and these clocks are really important. We're going to talk about this in depth. And these clocks are what set up the divisions or the bit timing. Without these, we have no communication. So in this case, what's wrong with this is the batteries are bad in the scan tool. When you plug a scan tool into a vehicle, guys, you've got to be aware that that scan tool now becomes part of that communication bus system. It becomes a piece of the network. So the individual who's trying to fix the car actually put a problem into the car, and you've got to be aware of this. At any point, when you put a scan tool on and you're creating a problem, don't think it's not the scan tool, even if it's a factory scan tool. I have all factory scan tools, and many times I've seen problems to where that induced a problem for some reason. Maybe the VCI has a problem, the vehicle communication interface. That's what interfaces the vehicle to talk to it, so we can encode and send messages back and forth, just like the very first frame we saw. We need a median and we need a transceiver, right? Something that transmits and receives. That being said, CAN controller area network, that's what we're really doing, but what is that really doing? Well, it's a networking system. It's multiplexing. It's a way to transmit digital signals between electronic components. We want to convey information between these components. We already know how all this works. This is done, and it has been for many years. So when we think about this, we can think about Morse code. Way back, we had the telegraph systems, and we had an individual sitting in an office, and you would take a message to him, and he would take that message, and then he would type out a message that would be transmitted down a wire, and another individual could encode that or understand what these dots and dashes meant. The dots and dashes are a way of encoding a system. All encoding, whether it's done manually or whether it's done electronically, the manual system obviously would be a telegraph system, but this is all automated now. But the same thing has to happen. I'm going to tap out a code, a mechanism of dots and dashes in Morse code. These dots and dashes compared to time, relevant time, bits, right? Because you'd have to know short, short, long, long, short, short, long, long. That's time, right? Now, we're cognitively processing this time, so we can actually look at an encoding, and we would say, you know, SOS is dot, 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 long, 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 dot, 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 so that's SOS. So now I have a piece of encoding, and we're going to do the same type of encoding in all of these communication bus systems that you find. Whether it's in a car or other types of vehicles, we're using the same fundamental things that we're going to do. These are found in automotive, manufacturing, military, automation, and industrial systems, communications, telephones. They packet data. When you talk, your voice doesn't go out as one continuous stream. It's continuously broken down into packet format, and a piece of what you said, a piece of the data, is put together, and then the frame at the other end is assembled with maybe 5 or 6 different packets of data, and it sounds like one continuous transmission, but it's not. These are all broken down into frames of data. The frame of data has references in it that tell it how to be put back together, what data we need out of this. And this, again, is going to be what we're going to be doing in cars. Why would I multiplex? Well, it decreases the size and weight of the harness. Now, we all almost got to laugh at that, but it's sort of true and it's sort of not. Because in the beginning, we have all these wires, and we want to get rid of the wires, and we want to make a smaller wire bundle. But when you look at all the systems they keep adding for the bells and whistles, it isn't like we made these wiring harnesses any lighter or smaller. They've actually gotten more complex with more complexity and weight involved. because I have so many new systems that I can incorporate once I've started to use these techniques. We're going to decrease the cost of manufacturing a high-tech vehicle, which absolutely is true. We no longer have or share parametric data. Sharing data, I'm going to show you here in just a second. So now I can send messages and I can share these, so I don't necessarily have to have wiring redundancy. We have better diagnostics. So now the system itself can keep track and it knows what's going on. So we can keep track of myself if I'm communicating as a node, or another node can keep track of me. So we're going to have a checking of each other. And we have much greater flexibility for adding a system. Let's say that someone built a car and now they want another system put on at the dealership. Well, I can simply install this new module and then tell the bus that this module is on there, and it will carry out a whole task. So this is flexibility that everyone's really interested in. This is sort of where we came from. So if you see this, we have this guy up here, and we have pin 7. Well, this would be like a K line, where I have 12 volts on that, and when I plug my scan tool on, I can have communication to the modules. But the modules may not communicate module to module. In other words, so if I've got the speed, well, let's see here. If I've got the speed sensor, well, he needs to go to the ABS, but doesn't the tranny need him, and the IC and the ECM? So I would have to have a wire that went to all of those modules. So each one of these systems, the crank sensor, the fuel sensor, the Prindle switch, the brake switch, these would be multifaceted. I can't have one module looking at this data. I need a lot of different information that's going to be shared. So I had multiple wires. Now this is a lot of redundancy, and this adds a lot of weight to the vehicle. So we wanted to try to get away from this, and so what we do is we start to do multiplexing. The multiplexing is where I'm going to take the modules and I'm going to interconnect these modules together where they're going to send the data. So now if I had the VSS is just going to go to the ABS. The ABS is going to broadcast the vehicle speed now on the bus. Now anyone that reads this on the bus can use it. When I say anyone, any module, the ECM, the IPC, the TCM, the ABS, they're all sharing. I can put one message on a bus and I can have the vehicle speed, and everybody that needs it will take that data and use that one message. So this is going to be way more effective for us in the long run for building vehicles. It's going to be way less expensive for one thing, and the car will remain lighter due to the weight constraints. This is sort of where we came from. So basically, hey, how do I? There we go. Okay, so in the old days, we actually have a switch. And if I want the light put on, I put a switch on, and that completes a circuit. Now I have a current path, and the current path is going to actually produce a load for me, or it's going to have the ability to work. In this case, we're going to work with a light. We're going to light a light. So this is going to be, there's something down here. I don't see it. No, there's something down here that's the screen doesn't show right now. Do what now? Oh, no. Oh, okay. Technical difficulties, I'm so sorry. Okay, now, down at the bottom, there's something. Yeah, I transferred it. Let's just see. It doesn't play it. No. Let's put it back where we had it in the other display center. I don't know why it's not showing it. So now if we hit a switch, you got to realize that the switch it's only a request. It's not a current path. So now when I put a switch on to have something applied, wipers, headlights, brake switches, whatever, these are only requests. So I send an actual request to a module. The module sends a message back to the rear, and now I turn on a current path with a different means. It's not a direct switch, right? This is directly controlled switching, not me switching it. So this is a whole different animal now, right? This isn't like where we came from, where we hit a switch and all of a sudden something happens and it comes on with a current path. Now I'm requesting the data. The microprocessor is going to send information on the bus, and it's going to make this apply. We have the SAE classifications. A Class A bus is basically going to have less than 10 messages per second. So this is something that's going to be a little bit slower system. We have Class B that's going to go 10 to 125 kilobits, and we have Class C that's 125 to 1 megabit. These are basically the time definitions of what I can do. So I'm going to have 10 messages on a slow bus, basically 50 messages, and these are maxing the bus out. So you're going to take these and you're going to cut them in half, because on any of these systems you're only going to run about half this time frame. So when it says that you have 10, you're going to be less than that. You say 50, it's going to be less than that. If you say 200, that's really only 100. Otherwise, the bus would have no space for any frames to happen. We need time in between the frames so we can take control of it, and we're going to talk about how we go about that. So in this particular system, now we are going to give some CAN standards. So the CAN standards, this is why CAN's used. You know, we all want to know, why did they pick CAN? There's lots of different really good communication networking schemes that work and give you high parametric data. The difference is CAN only sets a standard. That means it says that you sort of build it like this, and this is sort of how we want you to build it, and then the manufacturer can take it and put their own flavor on it. There's no CAN that says, this is the way that this is done. These are all sort of like driving. You're supposed to drive down the road, and I'm going to give you the set of rules. And the set of rules sort of means that I go sort of this speeds, and I can go on this road. But remember that the CAN speed on high speed goes from 125 to 1 megabyte. Well, any speed in there is CAN high. What does the manufacturer choose to use? The CAN transceivers are all internally adjustable. So when I buy a CAN transceiver, I can make it be 125, 250, 500, 1 meg. I just got to change a programming piece inside it, right? So now I can start to change or do what I want to do as an engineer at my company. And it's not that CAN says that, oh, this is the only way to do this. CAN is an open architecture. And since it was an open architecture, every single manufacturer can take it and make it their own. There's not one CAN that's all the same, guys. We follow rules, just like you have rules on the road, but those rules sort of change a little bit depending on how one applies those rules. So that's really where we got CAN from. And everybody took on to CAN because it's really an open field. So basically, if we look at some of these, we've got J2411. Well, that's a single wire layer. So what that's going to say is I'm going to use a single wire for my median, and then I'm going to have some rules that I'm going to apply to make it work. And if I look at ISO, so the ISO rule, 11898, now this is for high-speed transceiver. And then when we look at diagnostics on CAN, ISO 15765, that's like what we're doing with OBD2, right? So each one of these has a unique set, and it says we're going to perform in some of these tasks. But it really leaves a lot open for the manufacturer to make changes. And if we look at the heavy duty, so we've got J1939, well, that's going to have a different set of rules. So now, because my lines are so long, because I could plug into a trailer, right? And now these lines, and I have more modules, I have to run at a slower speed. We're going to talk about the bit timing edges, but these bit timing edges start to become really critical in order to process messaging. If I have really long buses, you can't run them as fast. You have to be slower when you do arbitration-style bus, and we're going to talk about what an arbitration-style bus is. So here we would have some examples: engine, transmission, brakes, suspension. Wouldn't you think that those things would be something that would need to be on a faster bus? So these are something that I would want to have a Class C bus for, something maybe working at 500 kilobits. And then if we look at it and we say, well, a radio and an amplifier, a CD player, we don't need very fast speeds there, so we're going to have a limited bus, something that's slower. And if we look at door locks and rear hood locks, how fast does the bus need to open your doors or your rear trunk? Do you start to see that each one of these has a unique set of working circumstances to where I'm not going to need the speed? Speed is money. The faster the bus goes, the more money it costs the manufacturer. So the manufacturer is not looking to spend any money that they don't have to spend. So if I can make this bus and I can split the bus systems up on the appropriate system, so I'm only going to have these high-dollar transceivers that go really fast in the modules that need them, in an engine control, in an ABS. Why would I have a really high-dollar transceiver to open a trunk or to put my wipers on? So we've got to all start to realize that what system you're going to work on when you're having a problem. Remember the problem. I requested a switch, and the switch only made a request that was carried out by a task in the micro. Now this starts to change everything. So if I'm trying to put a wiper on, is the wiper going to be on the high-speed bus? No. So you know that if you were looking at something and you had a multi-connection going into the steering column where you had high-speed wires coming into the steering column, those aren't for the wipers, guys. That's for the steering angle sensor. Because the steering angle sensor, I need speed. So once you start to think about this more clearly, each one of you needs to think about, what are you working on? And when you see wires, I was just at a shop where this guy was so confused because he had high-speed wires going in. They were for the steering column. You know, the steering position. They're not for the wipers. The wipers are on a very low LIN bus. So he's looking at the wrong bus to try to figure out his problem. I want you guys to not make that mistake. So when you think about this, you're going to look at what you need speed for. And then you're going to make an assessment on what kind of system you think it would be connected to. This is just a first analogy. We're going to use wiring diagrams, and we're going to do way better than that. I just want you to understand how we do this. There's a device called a gateway or a bridge. That's the proper name. A gateway is a means to where I have multiple transceivers in one unit. Now, if I have a slow bus, such as something I'm going to open locks, doors, windows, these type of things, it can't be on the same speed of the bus as something where I'm trying to control an engine or a brake system or a steering system. Does that make sense to everyone? Now these are going to work at two very different speeds, as we've already seen. If I have CAN C, that's 500 kilobits, but if I'm doing a trunk, I need less than 10 kilobits a second. Now what happens here is one bus moving at a very slow rate cannot be on a fast-moving bus, or we'd have collisions. That is data collisions, because one frame is moving way faster. We're banging out messages. We're banging out 200 messages on Class C at the maximum rate, but we're banging out 10 on another bus. Well, that's like having a Volkswagen Bug going around a Formula One track. It ain't going to work. You're going to have wrecks and collisions. I have to isolate these two systems. I'm going to isolate them with a bridge. A bridge is a way that I can transmit data from one side of the system to the other side of the system. So if I have a DIM, the driver information module, and I need what there? Well, I need RPM, and I might need vehicle speed, but where do those come from? Well, those come from the high-speed bus, right? So maybe I'm going to get the VSS from the ABS off of one of the wheel speed sensors. And maybe I'm going to get the RPM from the crank sensor, but the crank sensor isn't on a bus. He might be soon. Right now, he reports to what? An ECM, the engine control module. The ECM puts that data up on the bus. But I need it on the slow speed side of the bus, which is the driver information module. In order to do this, I have a bridge. This bridge, this guy right here, or gateway, is going to have my high speed connected with my low speed. So these two are connected, but inside this gateway, these are not connected. There's electronic circuitry that's inside here. One has a high-speed set of transceivers, and the other has low-speed sided transceivers. So it reads it on the high-speed bus, and it says that I'm at 3,000 RPMs, and then it puts it up on the slow-speed bus, or a slower bus, for the DIM, the driver information module, and then that is going to display this data. So this is a bridge, and this is really like central information modules, body controls. That's usually where this happens. Not always, but that's normally where my gateway is. When you look at a wiring diagram, you're going to see that you're going to divide the system into several subsets. Many cars could have multiple buses of different speeds, but every car is going to have at least a few speeds, 2 to 3 speed difference. These speeds have to be regulated. The regulation for each one of these that's going to make this occur is going to be the gateway. Now that we have this system set up, we have faster modules, the engine control, transmission, anti-lock, the steering wheel position sensor. These are on a high-speed bus. So this is going to work basically at 500 kilobits a second, where I'm going to be able to transmit data very rapidly. Then I'm going to have a lower speed bus, and this is going to be a bus between 10 and 125 kilobits a second. It's way slower, but I don't need the time. But we need to really understand that these are not the same buses. So when we're transferring data from one system to another, we got to understand, what are we asking, where's the data, and where did it originate, so I can try to understand what's failing. But first we need to understand that these are even on the car. So in this case, I have a central electrical module. Well, notice that the SIM has high-speed wires coming into it, and then the SIM also has this guy right here. Okay, so this is a low-speed bus. This is my high-speed bus, and notice what I've got over here for my cruise control dimmer switch, wiper switch. Now this is going to be something like LIN. Now LIN is a really slow-speed bus that's slower than what? 10 kilobits a second. So that's less than 10 messages. So I'm not looking for something that I'm trying to have super high speed. I'm just looking to be able to turn a wiper switch on. But the wiper switch isn't going to be on a high-speed bus, because that starts to cost the manufacturers huge money. If you have high-speed transceivers and the quartz crystals and everything that it takes to do communications, the cost of the vehicle goes up extra normal. So this is where we've got 3 different buses, and this is a real normal car right here. We have a high speed, a mid speed, and a low speed. They're all sharing data, but they're sharing it through a bridge. The perfect gateway, well, we need open flexibility. That means I need to be able to put modules in at the dealership level, high reliability in a noisy environment, the reduction of cost for manufacturing. We don't want it high dollar. We want minimum processing. In other words, you can load these PCs down. The micro can be loaded down by all the data it's trying to transmit, so we've got to be smart about how we're transmitting data and what we do. We need maximum program transparency, guaranteed data consistency, really important, short transmission times, and obviously the manufacturer doesn't want to add any cost whatsoever. So I'm going to have to weigh out these, and it's always going to be a pick and choose, right? The best scenario for the vehicle that we're producing or engineering right at this time. We have topology. So basically is what this is going to be, it's just the way it's laid out, right? This is how the system lays out. Each different one is going to tell me something just a little bit different about what I might expect from it. I can have a master-slave system. I can have a round robin or a token ring, and we can have arbitration. So one of the things that we can look at here is a star system. A star is where I might have a centralized module in the center and I could communicate to other modules on the outside. This is usually set up as a master-slave. So a master-slave is one where we have a node, that means microprocessor in the center, and I am sharing data with the outsides. But it's not exactly like that. Since the center module is the master, the other slaves can't do anything until they're asked to do it. So this isn't where we have open communications. This is where one module is in control of the whole system, and he's saying what's going to happen. The real low-speed systems, we're going to look at some of these. LIN. This is a master-slave system, and this is a very different kind of bus system. I can also have a slave that's not master-slave. I can have all the wires come into a center point and spiral out. And you've got to think about why the manufacturers are doing these kind of wiring techniques. It's how you build it. So if I did something like this, and I've just got to bring all the wires to a centralized point, it's easier to wire. Where if I've got something like a token or a round robin, this is a way more complicated thing because I've got to make a complete loop in the car, in the wiring, and I've got to have the wiring come back together. Think about you guys wiring stuff. Is it easy to get all the wires to go all the way around and come back and I've got a ring? So this is a more complicated system. The other thing is that I didn't tell you is this one, if I lose my master, if we have a master, the whole system is down. So this is not the best system if I'm looking for robustness, right? Because if I lost one module, the whole system goes down. That's very much like this system. If I've got one ring and I ground the ring, the whole system is down. So the way that we would make this is we would do something different. I would have a transceiver on this end and a transceiver on this end. A transceiver on this end, a transceiver on this. That's double the amount of transceivers per module. This gets very expensive. If you didn't isolate each section in your ring, if it came down, you pull the whole system down. So this is a more expensive thing. This is like most buses, right? It's expensive. It's not a cheap bus to make. So this isn't something that's generally implemented in most of the cars unless you have some kind of a high-end vehicle, just because of the cost factor that it takes to make it. A tree topology, this is what CAN is going to be and arbitration buses are going to be. So this is where I have them, modules just sort of set out, and I can stub them. I can have a main bus somewhere in the car where it's easy to wire in, and then I can stub them into that, and I now have communications. So a tree pathology is really good because this gives me the ability to make it cheaper and to make it work very well. It's also a very robust bus where it works well. We have synchronous. Now, synchronous is an idea of timing. That means that every module on the bus has a common clock. So I have one master controller that sends a clock signal out to all the other modules. Does that make sense now? Now, so each module isn't keeping track of time. I've got a master, and the clock is being shared between all of the units. This has a lot of edges. And if I have edges, lots of changes in, you know how we saw earlier, how you see these little bits and they come up and they go down? The faster that these buses are, the more radio emissions they produce. Every edge makes noise somewhere. It's radiating out from these systems. So if I have this, I've got a problem because now I've got a lot of noise. And in this system, I've got a common clock that I'm sharing over it as well. So I get a lot of problems with these type of buses. So this isn't generally used in cars. This is more like Ethernet. And this is what that would be. So this is a known clocking unit between modules. Now asynchronous, this is a totally different idea. This says that every single module on the bus keeps its own time. I don't have a master. I'm not sharing a communications clock. Each one has its own clock in it. This is CAN. So I have a quartz crystal in every single node. And every node is his own master. He's a master, and it's not I don't have a master slave. Each one is his own master. And he can take communications of the bus when he needs it. It's event-driven. So this is a very different idea. In clock synchronization, when I'm clocking off of a master clock, everyone's on the same clock and everyone's expected to have a message time where I send it. I send this message at this time, this one, this one, this one. So that's sort of how that's going to go, and I'm going to send information in known quantities in known time. Asynchronous is event-driven. That means that I'm not going to send a message till I need to send one. I'm not going to ask for data until I need it. That means I could be sitting idle and all of a sudden I need something, so I'm going to come up on the bus and we're going to try to have a conversation so I can get my data, or you're going to send me the data. I need to ask you for a request. This is going to be event-driven. Each module has its own clock. That means each module has to keep his own time. Now, because he has to keep his own time, guys, this starts to become one thing you need to really understand, and we're going to get into this. This is where a lot of your communication problems come from. The quartz clocks in each one of these units are different, and they're not all exactly timed correctly. I get 40 modules on a bus. I got 40 different clocks, gentlemen. 40 different clocks that are going down to microseconds to communicate. And if you miss a microsecond, you miss your communications. Temperature, age, all kinds of things start to change the clocks between these processors. Now the processors can't keep time. And I'm going to explain exactly what happens when they don't keep time. But that's what we're dealing with within a CAN system. Encoding is a way that we're going to send electrical pulses, high and low, ones and zeros, right? Boolean code, ones and zeros. It's the only thing that microprocessors understand. It's either high or it's low. It's either a 1 or it's a 0. Now, the 1 or the 0, I have to have a definite time in order to make sure what that is. That means I have to have bits, and I've got to know how long each bit is. This is all what's defined in the standards, right? So a lot of this is going to be set out. It's going to say, I need this bit time. We got to do this, we got to do that. But the bottom line is in order to do the encoding, I'm going to have breaks or divisions. So here what we see is we've got these divisions. Now I want you to notice that every bit, that's a 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 bit. Do you see how that every single one of these has a rise and a falling edge? This is very easy to keep track of when I have different clocks in different modules. The more transitions that I have, the more edges that I have to change. Every time I have an edge, I resynchronize the entire bus. If I have a falling or a rising edge, every module syncs to that edge. Does that make sense? Every module. When I start to have lack of edges, I start having harder times to keep track with all the different modules to keep the timing correct. Does that make sense? So what's going to happen here is a lot of the bus systems that we see, like this is going to be an encoding, and each one of these is going to make ones and zeros, and this is going to set a code. If we add Morse code for this, this is going to be my Morse code for SOS. And this would be in a system to where we could read that. So again, we would encode it, we could look at this, and then we would understand the encoding. Now this is variable pulse width, so this is like GM is going to use. Bits, I'm going to change edges. I'm going to have a lot of rising and falling edges. Every edge is a count to where I can keep all my clocks on. Every module is represented, he's got to keep his own time. Remember that. So if we have clock structures that start to fail, it starts to become really hard to keep that clock in time. So he's off. He's not timed with the rest of the bus. Now he's going to start to give you problems. He's going to set codes. And I'm going to show you exactly how this happens. This is just one coding scheme. This is pulse width modulation. So this is what Ford would use. And again, it's just edges. But note, every bit has a change. Now, this is why these buses couldn't run very fast. Remember when we look at variable pulse width and modulating pulse width, the bus speeds are much slower. They're 100 kilobits, 80 kilobits a second. And that's because we have all these edges that are changing all the time. But I can keep time, and I can keep all the modules in time really easily because I have these edges changing all the time. But I can't get too many edges because then I make too much noise. So I can't do that either. So I'm stuck here. Do you start to see that the encoding bits themselves got my speed stuck? So now is what we need to do is we need to start to look for another encoding method. So this is one that's called return to zero. So now I can go flat and I don't have to have an edge every single time. So I have less edges and I can actually speed my clock times up where I can transmit more parametric data. Now I go to something called that's non-return to zero. Now what this means is I can stay low or I can stay high for multiple bits. Now when you start to see that you have multiple bits, we got to really think about this. So if I had a whole string, if I needed 10 bits sent, we sent 10 in a row, but I don't have any edges to resynchronize the clocks on, and these clocks are having timing structures, can you start to see it isn't going to work? I can't go 10 bits. So what we do is we have something called that's bit stuffing. Bit stuffing is done in the CAN transceiver. The message will be sent out in maybe 7 or 10 bits, and the transceiver's job is to stuff a bit. The reason we're stuffing bits, gentlemen, is because you cannot keep time. You can't go more than 5 bits without an edge change. If you go more than 5 bits without an edge change, you'll have clock discrepancies across the bus. Now the message will be read incorrectly, and one of the modules will destroy the message. I'm going to show you how this works. You really need to understand this stuff because this is what's kicking your ass. This is the problem in your shop. You can't figure out what's going on, and this makes no sense. It really makes sense when you understand how they did this and why they're doing it. So this bit stuffing, I can't go past what? 5 bits. Every 5 bits I stuff it, and then the other side that receives it, the CAN transceiver, takes that out and puts the message back together. He's reconstructing it automatically. This isn't done in the micro. This is done on a bit level. So this is all done by the CAN transceivers. So this guy right here, this is just a stuffed bit. So we have, what's the rule? We can only have what? 5 bits. If we go more than 5 bits, we break a protocol of CAN. And that's how we're going to set codes in these. Okay, so the controller area network, CAN is a multi-master bus. That means that all of these bus systems, every module has his own master. CAN broadcasts, so he broadcasts, and when he broadcasts, every node on the bus is listening. So I have one broadcaster, but every other one of these guys is a listener. And then one of the other ones gets to take control and do its transmission. All the messages are assigned a priority or urgency. That means that it would be like if we were all waiting to use a telephone, and there was 5 of us, and I needed to call home to find out what I was having for dinner, and Chris here, he wanted to go find the tailor to see if his suit's ready, and each guy has a different idea. Do you see that? But now there's a wreck in the street, and it's with injuries. So the guy comes running up and he needs the phone, and his priority is obviously higher than mine or Chris's or whoever. Do you start to see that each module has an urgency, and we've got to set coding for that urgency. And that coding is going to take control of the bus. So if I'm an engine controller and I'm overheating and the body control turns my fan on high speed, I'm going to have a higher priority than other messages. So I need to take priority. I need to take control of the bus. I need to be able to use this bus to communicate with at this time. So what we do is we arbitrate for the bus. So this is an arbitration, or we fight for the bus. In other words, we contend for it. Each module can come up on any time they want, and if we have 5 modules that all come up at the same time, we have to be able to sort out who's going to get the bus. We do this with priority. This is arbitration. All nodes can access the bus at any time. Anytime I want data, I can go to it, because I'm a master, right? But I may not have the highest urgency, so my message has to wait to be transmitted. This is going to be done in priority sequencing. So this is how the CAN transceiver stacks the data out once you have the data. So let's say that we got a vehicle speed, a scan tool, a knock sensor, the RPM, and the oil temperature. And this is in the order that they came in. Now, in the order that we're going to prioritize this out, we have the vehicle speed, the knock, the RPM, and the oil temp. And where does your scan tool end up? Last. Scan tools have the least priority. The manufacturer doesn't need to run the car with your scan tool on there. He needs to keep control of the system. He's not interested in you using your scan tool. He could care less. He wants to make sure you have data, but your parametric data will be last. In every order, your scan tool is last. It never has high priority. It's the least priority of any node or module that gets on the bus. You've got to really understand this, because when you're using scan tools to get your data out, but you have latency or time between this happening, it really makes the scan tool work slow, and we think the scan tool's live. And that's because the people like us, we make the scan tools, and we go and we ask for data, and the data comes back. I put a point in time. So we time-stamp the point, or the data that came back to me, and then I put that on the screen. And now, this isn't like a scope to where I have a stroke that's going to happen every so much, and I've got data. This is random access bus, right? That means that if the bus has a lot of traffic, I'm not going to get my message back even though I ask for it. So now I get another point way down over here, and I ask for another. And then the bus wasn't as busy, so I put them right here. And we put linear interpolation. I connect the dots, and it looks like a scope. Guys, there's so much latency between these points that I'm getting back off of any bus system. You've got to understand the latency that you have in scan tools. It's huge. If you think you're going to find some fast-acting problem with a scan tool, you are making a drastic mistake. You need to understand the limitations of your tools. Scan tools have latency. And depending on how much the bus is active is how long your latency is. So in this case, you can start to see that the CAN transceiver organized the data, and then this organized data is going to be stacked, and then it's going to go out as it comes in. And it's prioritized. So the scan tool has the lowest priority. Just remember this. It's always important. We contend for the bus. The way we contend. We have two modules. Both modules, A and B, want to take control of this system. What's going to happen is A is going to come up and we start frame. In order to have the start of frame, we have to have 3 bits that are recessive. Recessive just means that we're at idle. There's no demand. We're not putting voltage up. Dominant bit means that a voltage change occurred. So if I'm at idle, I have the bus at rest voltage. And it depends on which bus. Which standard will change the voltages? We're going to talk about that. So right now, in this system, this is going to be maybe a high-speed bus, right? This is a 500 kilobit. So basically, this is class C. So here I've got bus idle. Three dead. I've got to have 3 that are low before I can have a start of frame. So if I end the frame, I've got to wait 3 bits, and then everybody can come up. So everybody was waiting for the end of frame, and then I've got 4 modules that all want to get the bus, so they all want to come up at the same time. I wait the 3 bits, and now everybody's going to go high. Now high just says that I've got to start a frame. That means I had a voltage change, and I changed it. Now node A and node B want this bus at the same time. Do you see that? We start frames. Now, after the start of frame, we have arbitration. Arbitration is where we're going to prioritize messaging structures so we can control the bus, so we know that we have the best chance to get the bus. Think about this. You're an engineer. You need to make sure that we have control of the bus and we can communicate on this bus. If all the messages could get the same priority, nobody could ever talk, right? One guy needs to win, and then the next highest priority will win the bus the next time, and then the next one will win the bus the next time. How do they win? Okay, I come high. So I go from from a recessive to a dominant bit. The dominant bit just means the voltage had to change, right? It's not at idle. So now I change this voltage bit and I come across. Do you see how I held the bit too high? Okay, B only has a priority of 2. Do you see how I went 2 and then the voltage dropped? Well, the transceiver is watching the voltage what's on the line bus. This guy kept the voltage high for another bit. Do you see that? As soon as this guy drops his voltage and there's still voltage present on the bus that's being read by the receive channel, he's lost the arbitration. He now becomes a listener. He can only listen. He no longer can communicate. He's not going to become anyone that can talk on the bus. He can't ask for information. He can't get it. He can't do anything. The only thing he does now is what? Listens to whatever's on the bus, and if he can use that data, he will use the data. But he is a listener now. Now, when this guy falls and he becomes a listener, this guy goes over and he held 2 more bits, and then he falls. Well, when his voltage drops at this point, and I get a drop on the read, now he knows he commands the bus. So now that he won arbitration, he's going to go ahead and send his message and his data. He's going to send an identifier out during the arbitration. So he's going to say, I'm the ECM, I'm the ABS, I'm the transmission controller. There's going to be data in this field right now. And this data in this field is going to say who he is and what he's doing, right? So this is basically how I'm going to win this arbitration. Now he's got control at this point. So basically, this is the way the message is going to be built. I'm going to have a start of frame. I'm going to have in a 2.0 CAN bus, that means I have 11-bit identifier. Do you see this guy right here? With an 11-bit identifier, that would be what I'm going to have. If I have an extended frame, I have a 29-bit identifier, and I've extended it with an 18-bit identifier. If I have an 11-bit identifier, if I take 11 zeros and ones, I can make 2,048 possibilities. That means I could send 2,048 different messages. If the engineers think I need more than that, that isn't going to work anymore. Do you start to see why I need an extended frame? Because 2,048 isn't enough. So if I put an extended identifier on here, I make over 536 million possibilities. So now I've got possibilities to where I can make way more definitions. I can say more in the headers. So this is the extended frame and a regular frame. A regular frame is 11-bit and extended is an 18-bit. So the RTR, this is what sets the difference. Whether I have an 11-bit or I have a extended frame with 18, basically I've got a remote transmission request. The remote transmission request is what separates the arbitration field from my data fields. So when I'm going to do a cyclic redundancy check that we'll talk about, the arbitration field is not checked. We arbitrate and we give some data up front, but it's never checked. That data isn't checked. What's checked is what comes after this. So the RTR separates it. Regardless if I've an 11 or a 29-bit identifier, RTR separates. Then we have some reserved bits. I'm going to talk about these in a bit. Then we have a DLC. That's not my diagnostic link connector. That's a length code. So that's my diagnostic length code. Okay? So that's how long I'm going to have my bytes over here. So in CAN, the most I can send is 8 bytes. That's 64 bits. So I can send 64 bits of data. That's the payload. Now after the payload comes, we're going to come over here and we payload this out, and then we have a cyclic redundancy check. We have a delimiter, an ACK, and then we have end of frame, and we end this. We'll talk about all this as we go through. I want you to look at how much stuff is going on to send 8 bytes. The overhead of these frames is extensive. To send very little data, I've got to have a lot in these packets or these frames of data just so I can deal with it, just so I know what I'm sending and how I'm sending it. and who's going to do what with it. So this gets to be a lot of overhead and a lot slower system. So this is the difference between the 2.0 and a 29-bit extension. So basically I have an identifier with an RTR ending the identifier, ending the arbitration field. Then I have the control field where I have the DLC, that's the diagnostic length, right? What's going to come next. Then I have my data field, I have a cyclic redundancy field, and we end the frame. With a multi-identifier, notice that I don't have the RTR here. I don't end it till over here. These two bits stay recessive, they don't go dominant, and that tells me I have another field of data coming. So that's the way this is going to be done. So that's just how it's going to work. Now that the node has won the control of the bus, we can see that we arbitrate. So realize that if you're arbitrating, and in the arbitration field, you know how we had a priority of node B and we had 2 bits, and we had node A had 4 bits priority high? Your scan tool has 0 bits. No scan tool has any bit. That means if any other module on the bus needs it, they get it. So then I've got to wait again. And now we come up with a couple of more modules, and well, they took priority because they had 2 bits. And how much do your scan tool have? 0. Then we wait and we arbitrate again. Except, you know, your scan tool didn't get control again because it's got 0. It's got to be an idle bus to get scan tool data. Do you start to see the problem here with thinking that these things are live? This is not a live bus. There is all kinds of latency in this bus. You know, I watch these people that talk about these systems, and they make it like it's live. It is not live. It is full of latency and delay. And the delay, you can't even figure the delay out. They make these really complicated algorithms, and they run them inside a computer to see how many messages might be able to get out. Because you can't even tell, because so many different modules could need it. Depending on the situation that the vehicle is being driven, run in, depending on what's happening, is how much the bus time is. So you can't calculate how long your latency is going to be. That's why you have X-by-wire stuff that's run on a clock, a master clock, where everybody has his own time because I can figure out my latency as an engineer. It's safer. This really works really well, but there's always a latency factor that I don't even know when I'm going to get my message through. So there's always urgencies. And these urgencies mean that I write a special frame that no matter what, it will be broadcast. Every system and every software engineer has these special codes in there for really urgent messages, and they'll take control of the bus no matter what. When I say no matter what, I've got to end the frame that's talking right now. Whoever had control of the bus, he's got to end it. Now the very next one, with the right priority, I win the bus, so I now can control the latency on really urgent messages, but I don't know what my latency is going to be in normal communications. The latency on your scan tool, guys, is the lowest, slowest, just the way it is. So when you think that that scan tool and those dots that I put together that look like a scope, that ain't no scope. That's hard to say how much latency is between each point. The more values you choose for your parameter identifications, the longer your latency is. So if you have something quick, don't have 10 PIDs picked, because I've got to arbitrate for every one of them. So when you say that you want a MAF, I arbitrate for the MAF. Now, I got the bus control, so now who did I go ask? I had to ask the PCM. He's got to take the data, he's got to process the data, he's got to pull that piece of data out at the point I ask for it, then he's got to arbitrate for the bus and send it back to me where I can get it, and then I'm going to ask for the TPS. And now I'm going to ask for your O2 sensor. The more that you have picked, the more latency there is between the points. So I make one point here for the MAF, I make one down here for the O2, another one for the TPS, another one for the APPS. Then I finally get back to the MAF to make my second point. Do you start to see that this is a circle? It's a loop that I'm requesting. The more PIDs you have in there, the lower their latency is going to be. So this is a problem for us. You just got to understand how it works, and you'll be ahead with these systems. So now that we've done this and we've controlled it, I need to make sure that this data is good. Because if you're sending bad data, what good would it matter? So basically, we have an error handling. We've got to handle the errors. We've got to be able to report them, recover, detect, protect, correction, and confinement. We can't just let a bad module go, and this is some of the stuff that gets us when we're working on cars because we don't understand it. Errors, how can these happen? We have inside and outside vehicle errors. We have inside ignition system, radio transmitters, right? CBs sometimes are in cars. You have cell phones, wiring problems, connection problems, node problems, alternator problems. All of these can give you excessive noise on the bus. The CAN is very good. I'm going to show you a bunch of different cars to where we have a lot of noise and they still transmit without any problem. This is a very robust system. We have outside radio transmission towers as adjacent vehicles, power plants. I had a customer at my shop. The car came in 3 times, kept setting these codes. I could never figure out what was going on here, right? So I was trying to figure out what problem do I got with the car. It had come in, I drove it, I kept it for 3 days, couldn't ever duplicate the problem. I went down to this lady's house and I met her. And I told her I want to ride with you to work. We drove by a big cell tower. When it went by the cell tower, codes. That's what happened. So don't ever discount that these external things. And sometimes to find the problem, you're going to have to go do the route or drive with the customer. It's sort of like those customers. You know how when they give you the one little tiny key that you just go in the ignition, you'd never see the problem. But when the lady came in and she had 20 keys hanging, and that would turn the ignition switch off because the weight that was on it, you could never see it until she drove the car. Many times, think about what you're looking for. Be focused on how to find these type of problems. We're going to go ahead and take a break.
Bernie, what can I say? I mean, I hate to even stop you. It's quick. This guy's the man. Smartest man in the business, I'll tell you that. Unbelievable. All right, so get ready. Our first thing from AE Tools is going to be a $300+
Nothing up my sleeve.
like an immobilizer type tool, I believe it is, a locksmith tool. And the winner is 2133736. 2133736. 2133736. Anyone have that number? 2133736. If you have it, good, okay. We got you, we'll stick it there. Next one is going to be an Actron auto scan that does a whole bunch of different things. And the winner is, I can't read the whole thing, 269007. 269007. 269007. Wave your hand if you have it. 26.
There he is.
All right. Okay, here we go. Okay, now this time I'm going to put a special high side extender service port for 134A and a Power Probe 4. By the way, this is not cheap. This is those hard to get 134s. It's by AirSep. And it's a yellow ticket, 248843. 248843. Look for your yellow ticket. 248843. Anyone have it? Yes, sir. All right.
picture or no?
Yeah. Next one, a Snap-on clock, 21-33528. 21-33528. You got it? All right, you got that and an extender. You should get an extra prize
Okay,
because you got up here quick.
there you go.
You know what? Maybe this will get people going. You just won $20 on top of that.
There you go. Thank you, sir.
See, we don't fool around.
All right.
So that means you'll walk up here quicker. All right, I'm going to do $50 cash from Pro Tools. So if you work in a shop where you don't have tool protection, or maybe you do, you really should have ProTech. $50 cash, right?
That's what it looks like.
Actually made in Russia, like everything. Okay, here we go. Whoa, a yellow ticket again. 248863. 248863. Wow, you got $50.
Oh, here.
Wow, nice. Chris Bill. All right, I'm going to do another 50. Just because I'm a nice guy. All right, this one's fake, by the way. This one's made in China. Okay. 270186. 270186. 270186, sir, coming up. Who, Jamie? All right, two more of these. Don, get me those clocks. We're going to do another AE tool, and I don't know if this is the one we have in the shop, but it works good. 2696633. 269633. 269633. Anyone? All right. Don, go check him out.
You got that?
Nope. Clock time. What time is it? Snap-on time. Look at that. See that? Jim told me to say that. He paid me extra.
It's awesome.
All right. 269922. 269922. Good. A gentleman back there. Neil? All right, a can-do battery system tester. Think it's about $400 or $500. Here we go. Oh, yellow ticket again. Look at that. You get paid to like come out. Amazing. 248367. 248367.
He's coming.
Guy coming up. Excellent. Here's New Jersey's own.
Can I give this to somebody else?
Why? Wrong ticket?
No, it's good. He just wants to let somebody else have it.
Oh, that's a very nice guy that's letting someone else have it, but he did say something about Mac tools. No, I'm only kidding. The bad word. I'm sorry, Jim. So, Mandy Concepcion has a great tool, a bi-directional tool. He couldn't make it out today as a vendor, but this is a really nice tool. Go visit Mandy's site. It's probably $300-400 bi-directional type of tester where you can put stuff. You know Mandy. Okay. He makes some good tools. So here's one of his tools, 2133981. 2133981, about a $400 or so tool. All right. Excellent. And we're going to do that nice clock back. That was very nice. Oh, I can't pick. I'm sorry. What do I know? I can do anything, but not that. I can't pick. 269274. Go see Doreen. 269274. I think we got someone?
We got a winner.
All right. I like that. All right. Let's do an easy red light. Goes on your head when it's dark out. You know how the lights go out around here? So here we go. Yellow ticket. 248424. Another yellow ticket, 248424. All right, a gentleman in the back. Is that Bear? Oh, sorry, you can't win, Bear, if that's you. No, I'm only kidding. I'm only kidding. All right, AES Wave Kit. Now, Jim Morton, this has your name maybe written all over it. Oh, nice. Look at this. My buddy George Menchu, who couldn't be here, his wife's not feeling well, but he donated a couple of things in his great little lab scope kit. It's a great kit. Speak to Pete Meyer about it. And here we go for Menchu's kit. 21-33-842. 21-33-842. We got someone? Jamie? All right. All right, what am I going to do this time? We'll do an Actron. This resets all different airbags and brake system, bleeding, all that good stuff. 21-34480. 21-34480. All right. We're going to do another Joey and Mike special there from AE Tools. And this number is 269111. 269111. Wow, right up front. Doreen, we have a guy right over here. Oh my God, here's. What, did you buy the whole place out? And that's all you won? You got the Maloykia. All right, Bartek. This is about $1,300. I'll have to take a picture of this. This is their new TPMS tool. Nice setup. Yellow ticket again. Yellow ticket. You know, Mary Partington, I feel like this has your number on it, because you always win. 24-83-71. 24-83-71. Anyone? Come on, where's the guy that won it? 24-83-71. Oh, we need his picture. You got it, dude? Is it your first time here? No?
Been there all 15 years.
You're the man, and I don't know you? What type of crap is that? Fire this guy. Let's get a picture of you. Thank you for coming from, were you, Syracuse? Or?
SNS Auto.
Oh, SNS. Secaucus. He's a New Jersey boy. Congratulations, man. Thank you. All right, snap-on clock. Here we go. 269449. 269449. Someone go back to CPS back there and get what they have. They got some stuff to raffle off, or just relay what it is. 269449. One more time. 269449. Is that a hand up there or bad armpit smell? Someone coming up? He comes up slow. He don't get $20. But you got a clock. All right, another AES thing here, I believe. Oh, this is that good piercing kit. The George Menchu, this is a nice set. This is all the connectors, so you don't need to pierce wires. Watch yourself.
Yeah, nice.
Look at that. Feels like I'm on vacation. Oh, Chesney's trying to come up and slip me some money for the kit. Get out of here. Yeah, this is a great set.
Yeah.
All right, we're going to have to take a picture of that. And the winner is Tom Rake. I figured I'd get Chesney, wake him up. Oh, woo! 21. You don't need that hibachi table. I better keep these away from each other. 21-33305. 21-33305. 21, right here. Excellent. Let's come up and get a picture of you. All right. This is a good set. This is really a nice set. Oh, yeah. He sold this big time. Just hold that a second. Let me see your ticket. Good for you, man. Good for you.
Thank you.
Best of luck, man. Thank you. Thanks for coming out. All right. Let me see what I'm going to pull out of my hat. You know, since we have the Bernie Master up, it's a yellow ticket. It's another great e-scan. This tool for drivability, I was just teaching down in Philly, a trainer, and I got to tell you, people go, what is that tool? This is an amazing tool for drivability. Doesn't take the place of other scan tools, but it really is good. And Bernie, what's the retail? Bernie, what's the retail on your eScan Pro? Elite, whatever it is, I'm sorry. What's the list price? $1,600. So look at this, another yellow ticket. 248827. 2488. John Rogers. Mr. Rogers' neighborhood, all right. All right, John, Long Island man. We need a picture of you. Look at that. Oh, John, you lied to me.
Wouldn't be the first time.
Congratulations. Thanks for coming again.
Thanks, Jake.
You're the best.
Take care.
All right, one last one, $50, and then we got to get Bernie back. Another yellow ticket. 248349. 248349. Now we got a lot of big prizes left, including the Flow Dynamics Air Vac that really kicks butt, works real well. But I got this nice $50 bill. And then we're going to do, if you put your evaluations in before, you're going to be text, okay? You're going to actually be text if you're a winner or not, and you'll have to see me for the cash. So if you didn't put it in, you're like this guy, Bobby Mace, who could get lost anywhere. Give Bobby Mace a round of applause from Transmission Digest.
Give me 50
Good man.
bucks.
Yeah, quiet. Buy me a drink later. All right, here's the number. Thank you for coming back. 248349. 248349. 248349. No one has it? Anyone? Wave your hands. Jump up and down. Nobody. Last call. 248349. Sorry. Next ticket. A white ticket. That sucks. Someone didn't look. 21-33911. 21-33911. Come up for the $50. All right. Courtesy of ProTech. I guess he's coming up, right? All right, let's get Bernie back on. You heard enough of me yakking. Let's get back to some good stuff. Got to be around later when Bernie's done. We have the last raffle. In the meantime, if you want to buy raffle tickets, there's some real good prizes, including that real big one from one of our main sponsors there. Actually, we have two good tools coming up and more, but $23,000 plus, almost 24 grand. So, Bernie. All yours. Thank you.
Thank you, G. You know, what an amazing event. Here you can come and you can learn and you can win a $24,000 Autologic too. It's hard to believe. Only G could pull this off. So where we're talking about, I had a couple of questions at break I want to clarify real quick, okay? First off, I had a couple of people ask me about synchronous. That means I have a master clock that's in order. In all of these protocols that we covered, these are all asynchronous. They're arbitration, event style driven. One of the few buses that's in a vehicle today that actually uses a synchronous system with a master clock is FlexRay. FlexRay is a new standard. It really falls under something called X-by-wire. And there's a bunch of different systems. FlexRay is one of those systems under X-by-wire. That system has a clock that has a universal timing to it. But in like pulse width modulated and variable pulse and all the stuff we covered, be very aware that these are event-driven buses like CAN is, right? Except the speeds are different because we have so many edge changes, right? So they're all very similar. So you can take a lot of what I'm telling you about CAN, and obviously it's not the same because there's different standards, but the arbitration fields, many of these things work out to be very similar, okay? That being said, we have errors we're talking about. We have basically global errors and local errors. What's the difference? A global error is some noise or something that makes a transmission voltage change, and it changes over a longer period of time, more bits. Where I have a local error, where I could have some noise that would come up and change a bit, and I'm only changing a bit. Now this might not be able to be seen by all the modules on the bus, because remember, I could have up to 40. CAN standard says you can have 40 modules on the bus, right? So what that means is if I have this little tiny noise, I might only see this with a few modules, not the whole bus. Something that has a larger noise span on it, I'm going to see on the whole bus. Now we've got to figure out how we're going to find these and deal with these. The first thing is a CAN bit. So the CAN bit is going to be set up by the speed the CAN system is working on. Obviously, a CAN system that's working at 125 kilobits isn't going to have the same bit length time as one that's working at a meg. Does that make sense to everyone? The speed is much different. So the bit length, first the engineer will set this up and he'll know this. But what we're going to end up having is we're going to have these divisions. This is the rising edge, and it comes across and say a falling edge. And we'll talk about how these work, but basically I'm going to break these into quanta. The quanta is breaking, this frame or bit is broken into 4 basic pieces. The reason for this is we're trying to keep the bus in time. Remember, the edges and the clocks are all different. Everybody's got a little bit different clock, and I can't get clock drift. If I get clock drift, that clock, the guy that gets the drift, will ruin my message. He'll destroy it. I'm going to show you how that's going to happen. So in order for that to happen, we do not sync on an edge, the first edge. There is 2 types of synchronization, hard synchronization and soft. Hard is where as soon as we start frame, everybody starts a clock and they're all trying to keep time to that clock. That's hard. Soft is every edge that I have in the message is trying to keep synchronization. That's soft synchronization. When I have an edge change and I have a bit and I go up and then we come across, I've got to give a bunch of time so when I count it, I didn't count on the edge, but I count somewhere towards about the 80% mark, and that's where I say that's a bit, that I went high. That way, I give the guys who are lagging or slightly behind time to resynchronize. Otherwise, each bit gets out of time. And if we get bit timing errors, we have problems on buses. That's where the clocks differentiate from each other from one module to another. This is just an idea of how this is actually done, and it's done with quanta. We count over a number of quanta. There's 2 different processing clocks that watch quanta. We won't get into all that because it's not going to do you any good, but the ideas that I'm expressing here, I'm going to put all of these to work when we start to work on cars, and you're going to understand why I went over it in the order that I did. The CRC, this is a cyclic redundancy check. The CRC, I've got to have a way to check the message that was sent. We built the message and we argued for it. So modules come up, they argue. One guy gets the bus, one node or module. He now orchestrates his data field and he puts the data and the bits in order. Now, at the end of where he's done here and the data field is complete, I have to check the data field. In order to check the data field, I run a CRC. This is 15 bits plus 1, 16, because I have a CRC delimiter. So this guy is going to tell me what message, if it's good or not. Now, this is so complicated, guys, that this is done in the hardware. As the bits are cycled out and as the bits are being put together and arranged, or the message is being sent, the processor that has control of the bus is running a cyclic redundancy check through hardware. This is going to make a polynomial. Now, a polynomial is just a mathematical equation, and it's going to divide down to a known quantity. And it actually comes to where we divide it down to where we have two strings of data, and we compare these two strings, and if they're not the same, we had an error, a bit error. Okay, so that's sort of the way that that's going to work. The idea is cyclic redundancy is only checking the message. If we don't confine or do anything else with it, it's just checking it to say, is it good or bad? Because we don't want to have a message out on the bus that was bad, because if you said that you're going 200 miles an hour and you're going 30, we would have some type of an error. Maybe we would want to do a speed limiting error because we thought we were going 200, so we would shut the injectors off to try to limit the speed. That would give me a problem. So we don't want bad messages on the bus. We need to contain the bad messages. The CRC is just a code, and it's going to go in and it's going to check it. Now, the other modules that are receiving the messages are also running those messages through their CRC. Again, this is in hardware and part software. And if they see that the two errors, the strings, don't line up correctly, then I'm going to have a problem. They're going to say that the message is no good, and they're going to destroy the message. So that being said, what this is we have a CRC field at the end of the data field. The CRC is what? It's checking the data field to make sure that we don't get bad messages. Then basically is what we're going to have is we're going to have this CRC delimiter. That is going to be a recessive bit. If it goes dominant, it says that you have a problem with the frame, and then it violates frame form. So basically, we come across, and then we go to the next piece. And the next piece is an acknowledgement. This is referred to as an in-frame response or an acknowledgement. So in CAN, they want somebody to be able to say that they heard the message. I got 40 modules out there. In real cars, we might not have 40, but we're going to use that as an expression. Might have 3. It really doesn't matter. I need somebody out there to acknowledge they got the message. Now, there's no way that they had any time to evaluate the message to know if this messages are good or bad. That's not what this is about. This is about the module that's sending out the message goes recessive on this bit. He's not putting anything out, and somebody else that's on the bus puts a dominant bit here. They change a voltage state. He didn't do it, somebody else did. Does that make sense? That means as soon as he sees that the voltage went high when he didn't put anything there, somebody heard the message. That's all it means. It doesn't mean that the message is good or bad or anything else. It just tells me that somebody heard it. It's an acknowledgement only. But this acknowledgement is going to be very important for you guys to understand how to fix the cars. So this is an acknowledgement. Who puts the message? Any other module on the bus. So this acknowledgement, we have positive acknowledgement. Positive acknowledgement states that just, it's a good thing that somebody heard me. And then we've got a negative acknowledgement. A negative acknowledgement is where I don't put anything in the frame. In other words, I don't get a response. Okay, now this is important, guys, because if I have CAN C, I have in-frame acknowledgement. If I have CAN B or CAN A, there are no acknowledgements in the message. There are no acknowledgements. That means I don't know if anybody heard the message or not. I broadcast it, but I never was told that I had someone hear it. So I'm broadcasting, but I don't even know that anyone could hear me. These are differences in the bus, the way that the structure is going to be. And this is important for us to understand when we're fixing these cars. So an acknowledgement is just going to go up. And who puts it up? Another module, but not the guy that has got control of the bus. He arbitrated, he sent his message, he did his cyclic redundancy check, and now he goes and he does not put a bit there. So he stays recessive. Someone else goes dominant, puts a bit there. He says, okay, somebody heard me. So now, This is what happens when you don't have an acknowledgement. You have a repetitious frame. And this repetitious frame, he's looking for someone. Did anyone hear me? Did anyone hear me? Did anyone hear me? Well, when you get on a bus and you cannot talk to a module, and you're going to have to check the wiring, and we're going to go through this on a bunch of cars, you got to put a scope on it. And when you put the scope on it and you see that, your wires are broken to that module. No one can put that acknowledgement bit in for him. Now, nobody's arbitrating him, so he gets the bus every single time and he puts the same message up. Can you hear me? Can you hear me? Can you hear me? No one, this will go on indefinitely. So when you get onto a module and you see repetitious waveforms that look identical, what do you know? You know that no one can put a bit in, and if they don't put an acknowledgement bit in, he keeps asking for it. I got a wire broken. That's what this is. And I do a lot of these, and this is the way you see them. You will also see this on other systems other than CAN. They all have acknowledgement on the higher speed stuff. So you need to be aware of this. So this is something I need to be aware of. Message acknowledgement. This is really important. If I have a CAN C bus, I expect a message back. When I send something out and I'm asking, you're going to have to argue for the bus, and you're going to have to send me back a message saying that you got it. I ask you for something, now you need to send it back, or you need to give me a response saying that I sent you a message. Did you get it? Oh yeah, I got it. It's expected. On CAN, B, and A systems, no response is necessary. They do not expect it. There is no in-frame anything for this. So what does that mean? That means if you're on a CAN B bus and you have a module die, do you know what? You have no code. The guy's dead. He isn't even on the bus, guys. He died, but he died all at once. Does that make sense to everyone? Well, no one expects anything back from him. So you have no codes and the guy's dead. And you're wondering how that could happen. Well, the reason that that can happen is because there's no acknowledgement and there is no frame for me to get back a message. So you could have a DIM, something like a driver information module, the dash, and the dash is totally dead, and you're trying to figure out what's wrong with it, and there's no codes, and none of the other modules on the system are set of code, because in CAN, we shoot the messenger. You're going to see this. The guy who got control of the bus is determined that he's going to be the failure. And that is because the way that this system is set up. So I'll get there. But you need to understand that you can have a module that died with no codes if he died all at once. And no one set any codes prior to him dying. I had this car in 1998. Volvo. Dem is dead. And we're trying to work on the car, and we can't figure out why no one has codes. That's when I started to get the papers from the SAE, and I started to read how these systems work, because I'm not going to get my butt kicked again by the same problem. Then I started to understand how the stuff really works. That's what I'm trying to share with you. So you're not trying to program a dash that's dead. We program this dash with factory Volvo software. Says it's successful. Is it successful? No. It said that the program was able to talk to the sim, because that who establishes who I'm programming with, right? Because you're going to go on and you're going to tell everyone that get off the bus, because now you're going to program it. And now we're going to start to set a string through the system to where we're not arbitrating, but we're loading a program, right? We can't have a bunch of noise on there. Well, what does it mean it was successful? It meant that it was successful in moving the data. It didn't say it was successful in talking to the dash. That's what you interpreted it as. So now you think because you programmed it and it was successful, you could talk to the module. Dude, the module's dead. He's not even alive. And you're sure he's alive because the factory said they could talk to him and he was successful. Start to understand what I'm telling you. You got to understand some of the really weird stuff in this CAN bus, or you're going to really have some bad days. Bit error. So I can have a bit error. That's the bit received is not the value transmitted. That's a CRC check, right? Checking the bits. And we're going to check, we're going to do a CRC, and then we're going to look at two strings, and the strings got to match up. Basically, bit stuffing. How many bits do I have to have in a row? I can never violate 5 bits. If I go to 6 bits, it destroys the frame. That's how they say that this frame is no good. We have a cyclic redundancy. Again, that's going to check it. Form error. A form error is from the CRC delimiter or the acknowledgement. So if either one of those bits are bad, it's a form error. So basically, these are the ways we're looking at it. Now we're going to go to the end of the frame. We've determined that the CRC didn't come up right. I've got bits that are incorrect. In order to make sure that this message cannot get on the bus, the guy who is transmitting the message has to destroy it. He's going to destroy the message by holding the end of frame more than 6 bits. If you violate a 6-bit rule, that means that that frame is no good. That is a global error. So when we come up to the end of frame and we only have 5 bits at the end of frame, that says the message was good. If we have 6 or 7 bits all held dominant, that tells every module on the bus to not look at this message. This is a bad message. Now, so I don't have to argue for the bus again. I end the frame and I immediately get the frame. There's no arbitration. The guy who fails the frame gets the frame again. Now, I fail again. Now I fail again. Now I fail again. Now I fail again. Can you see how this could just eat all my bandwidth up on a bus? So there's something else that's done. And that is that there's another slot over here at the end. And this is the error delimiters. There's 2 bits. Those 2 bits can be put in by another module. So if I'm in a passive state, I'm not actively flagging, I'm passively flagging, that means that I failed 16 times. If I get one other module that puts another piece right here, a bit, I'm kicked off of the bus and I can't talk, but I'm not kicked off. I still can listen, but I can no longer broadcast. This is the way they don't just tie the bus up, because if you have a bunch of noise and there's a bunch of problems, we would never be able to transmit any messages. So I've got to be able to control it. So I'm going to allow it to go 16 times, and then I'm going to get another module to put a bit in there, and then I got to shut down, and I can't do anything for quite a length of time. It's a number of messages before I can come back on the bus. That's trying to limit, if I have a bad module, to destroy all my buses, my messaging, right? I need to contain that. And that's what this is about, this end of frame. And that's what the error delimiter is. The error flag, the original flag, is going to be held down by who? The guy who's talking on the bus. Now, another module, he can put in an error delimiter here. But once the other module has gone passive, he's no longer active, he can no longer put a bit in. So if we've got a bus with a bunch of broken stuff, and they're in error passive modes, they can't destroy the other module's signal anymore. Now let me tell you, this is really important right here, because this is what really happens on the bus. The clocks get off. And when the clocks have a problem, or the temperatures are different, and my edging isn't correct, I will run a CRC, being another module, and I'll see it came up wrong, and I'm going to put a bit right here, an error delimiter, and I'm going to destroy your frame. Except I don't get counted for it. I ruin your message, but no one counted me. Who got the bus? Oh, I'm the ECM. We said that was the identifier in the arbitration field. We got an RTR, that's the end of that portion, and now we start the transmission. And that message transmission is who is doing the cyclic redundancy check isn't done on the front part of the message, right? It's only done after RTR. Now I look at the message, and the message came up wrong, and I'm another module. You're broadcasting that message. I'm another module. I ran a CRC, and I think you're bad. Well, it didn't because it's bad. It's because my timing edges are messed up. I'm not in time with the bus anymore. And now I go and I destroy your message by putting a bit there. Everybody says it's a global error, and you get a count against you. Do you start to follow this? Now, I'm starting to get all these counts until I get coded, but it isn't me. It's one of the other guys that his clock is broken. That's what happens here. And this is a really common problem where clocking issues, because you're dealing with microseconds for these edges. And you're dealing with a bunch of different wiring of different lengths and temperatures. And you can get different kind of ringing, and you can have all kinds of problems that can give you bit transmission errors. And I can keep destroying other people's message. This guy, oh, well, I destroy him. He's bad. And then I destroy him. And, well, who never gets destroyed? Me, because when I'm on the bus sending the message, my clock works. I'm destroying everyone else's message because I'm listening, and my clock is incorrect. That is one of the ways that this is a sort of a bad system, and this is how we shoot the messenger that sent the frame. Each node maintains two error counters, a transmit counter and a receive counter. The transmit counter detects faults incrementing the transmission error. So basically, I'm going to count faster transmitting rather than receiving. This is because they think the transmitter's the one that's going to be the failure. So basically, for every time that I do a count, if I am sending the message, I get 8 counts. For every good message I send, I get to take away 1. When I count up and I get to 127, I now am in passive error. That means that I can no longer destroy anyone else's data. I can destroy my own, but I can't do anyone else's. Error active, that's when you're below 127. So the counts, I haven't had a lot of failures. The more failures I get, right? I got all these failures. And these failures is what they're doing is they're saying I'm bad, I'm bad, I'm bad, until they're trying to limit the damage I can do. So they just put me in a mode to where I can't destroy anyone else's message. I can't say anybody else is bad. I can only clock myself. And then once I go to error passive, that's over 127, and at 256, I get kicked off the bus, and that's permanent. You cannot get back on the bus once you're kicked off. I'll show you how you get back on. So basically, a transmit error gives 8 error, receive gives me 1. Every time I do a good message, I get 1 point off. So I'm accumulating, but I'm also deducting, right, the whole time. And there's lots of errors on a CAN bus, guys. That's normal. What's not normal is to let a message get out that would be corrupt. So this is what this is about. This is about controlling corrupt messages to not let them on the bus. So basically, this is just a scheme. And the scheme says at 127, after 16 attempts, you no longer can destroy anyone else's message. You're passive. Before that, you're active. You can do someone else's message or you can do your own. Bus off state. You're going to have to require a long, long time of where you have idle time. It will never happen. So in real world, your only way you're going to get back on the bus is a hardware reset. That means putting the 2 battery cables together and draining them. Let me tell you another story. I go to shops. They go and they put a new module in because they couldn't talk to the module, and then they can't talk to the module when it comes back in a month. Well, guys, it wasn't the module the first time. He got kicked off of the bus. Before you start saying that the module's bad and you can't talk to him, you might want to do a hardware reset and see if he comes back to life. Because if he comes back to life, he was put in bus off state. In a bus off state, he cannot communicate. He's exiled. They're going to limit the damage he can do. By 256 points, they figure that this guy's so bad that he's just destroying the rest of the messages on the bus. So he no longer can do anything. He doesn't listen. He doesn't communicate. He's off bus state. So I've had a couple of shops that have put modules in, and now they got the same thing. So they call me, and I go look at it, man. The first thing I do is I do a reset, and I can talk to him. Well, he isn't the reason that everybody's off. There's codes for everybody. He just got the most counts against him and got kicked off first. Do you see that? So you got to be careful about this. This confinement state, basically, I'm going to set code somewhere, depending on the engineering that did this, somewhere around 96 to 100 counts. That's DTCs. I passive error at 127 and I bus off at 256. Fault containment. We can find a faulty node on the network. We want to confine him, right? We don't want him doing any more damage. Isolates the faulty node, and it needs to do it quickly. You can't have him just totally disrupting my messaging. Distinguishes between temporary and permanent faults. And I'm going to allow a guy that's sort of bad back on, right? I'm going to confine him, and he can get back on once he's gone through enough transmission cycles from other modules. He no longer can transmit. Permanent off, he's off the bus until there's a reset done. Error recovery, this is all handled under the protocol. It depends which CAN system you have. CAN C, this is high speed. So this is 125 to 1 meg. Usually high speed is going to be 250 to 500. Again, this has to do with an engineering crew that's building it, right? I can do anything between these speeds. That's one of the reasons CAN is so universally used. This is a carrier sense multi-access collision resolution. That means that we can do all the things we just talked about, right? That's basically what that says. This is the transceiver. We don't need to get real involved, but we can see the 120 ohm resistor on one end. Realize that that can be external or internal into the modules. You don't know where it is until you start looking or you start reading on where they've put it. We have basically at a 2.5 volt, and we're going to go up a volt and down a volt basically, right? So this is going to be where one voltage goes up while the other voltage goes in an opposite direction. This is how the actual transceiver is going to handle this type of communication and how the voltage is made. We don't want to get into all that, but it's there if you want it. The CAN high speed uses two opposing voltages. This is to reduce emissions, guys. Remember how we first talked about, we said in the pulse width modulating, a variable, that we have too many edges? And these edges make radiated emission. Anytime you have a really fast changing edge in any electronic structure, you have radiated emissions from it. The faster the edge changes, the more noise you got. Well, we don't want noise on here. So to make the bus go faster, I'm going to use a two-wire median. The two-wire median allows one voltage to be opposed to the other voltage. This cancels out noise that would radiate out from this that could get into crank sensors, cam sensors, other systems on a car that would give me drivability errors. So we wouldn't want that. So we need to figure out a way that we can make a bus go really fast. Remember, we talked about these other buses that we had prior to this. The variable pulse width. It's 80 kilobytes. These are really slow. This is what we would call CAN low speed almost, right? And the reason is because they have so many edges. I get rid of the edges, I can make it go faster, but now I still need to be able to limit the amount of change. Well, that's by having these wires and having a double wire system and having the voltage oppose each other, and that is going to limit my emissions. In order to do that, we twist the wires together. Now, the twisted wire works both ways. It keeps it from going out, but it also keeps it from coming into this channel. Twisted wire is just a way to limit my RFI. And the RFI is 20 hertz to 3 gigahertz. That's just radio transmission. But that's just saying that I can make these noises, and I could get it into the wire, I could get it out of the wire. When we twist them, we're going to reduce that. This is a CAN signal, so this is CAN high speed. So basically, we can see that we have brakes here, and we can see these brakes in between here. That's my 3-bit idle period, right? In other words, the bus has to go idle before someone else can take control. When you see messages that are just lined up, boom, 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 they're all waiting to do messages. When you first turn the key on, and you've got a scope on it, you watch it, peg it. All you see is solid transmissions of messages where everybody is trying to get on to do their message carrying. After a little bit, it will go and you'll have some idle time. When you see some of the high-end cars that have 2 CAN buses, it's because if you have this, you have no way to arbitrate. You can't say how long it's going to take to get control of the bus. Latency would go through the roof, right? So I need 50% idle time at least. So when I get enough messages on the bus to not provide me with 50%, I add another CAN bus. That's why I have multiple buses. It's because the arbitration fields, I can't predict latency anymore. If you overdrive the bus, you no longer know when a message is going to get up, being an engineer. So that being said, I'm not going to do that. I'm going to add another bus. That's why BMW has 2 buses. And that has to do with the latency and the way that we argue for the bus systems, the structure of the bus. I want to make a note. Do you notice how you can see that this is lower than this? These are different modules. Always look at the bases. Look for slight changes. And that's just telling me that I see different modules happening, right? That's one module talking, and that's another module talking. It's not the same one. When I change ground or voltage elevations, that's a different processor talking. So I'm trying to figure out who processor is failing. I'm going to show you how I'm going to do this. Termination resistance. I got pin 6 and pin 14. Pin 6 high and low. So basically, I'm going to need to terminate this. If I have a 120 ohm resistor and we have a circuit like this, we can do this mathematically really easy. So we're going to look at our total resistance, and we have 120 plus 120. We're going to divide 1. That's 0.08, 0.08. That's 0.016. Divided by 1 is 62.5 ohms. That's your overall resistance, what it should be. Just know somewhere around 60 ohms and you're going to be okay. Termination resistance is within the system. The termination has to be there for proper communications. This is just showing we're checking it on the car. Again, you cannot have the car powered, right? The bus has to be dead. He had to go to sleep. If you got voltage on the bus, you can't ohm anything. Can't ohm anything in any circuit with voltage on it, guys. We all know that, though. We're professionals. The termination resistor, the high-speed CAN bus must have termination resistance. We're not talking about this as just a nice little idea. If that termination resistor isn't there, you have echo. And echo is ringing. And the ringing will give you codes that you'll blow your mind. I've seen a couple of these cars that I've worked on where they only have one termination resistor, and they're ringing and they're setting codes for everyone. And that's what's wrong is you got a termination resistor missing. So, or you got a bad connection to where one can't be made. There's several ways we can get this, but what do you absolutely know? You have to have it on high speed. You don't have to have it on CAN B and C. You have to have it on a high speed because the bus is working so much faster. This is a ringing. So if you don't have termination resistors, that's what you see on your scope. All you see is ringing. The energy is ringing. Rather than making any kind of a steady kind of signal, it starts echoing or ringing, and that's what you see on the scope. If you see this pattern here, you have multiple modules on the bus, and you've lost your termination. If you have one processor, you won't ring. If you have more than one, you'll ring without transmission, without the termination resistance. So basically, this is how we would have this set up. I want to make a note that you guys absolutely need to listen to. When you see a scan tool where you're not communicating on that bus, but you're communicating with a SIM, You may not have termination resistors, guys. That module blocks you from it. If you've got a Jeep Chrysler product, they block you. The front module, you're not on the bus. Let me be clear here. Those wires, when you plug your scan tool on, you are not on the bus. You are isolated from the bus. You are using the bridge mechanism to bridge your scan tool onto it. That means I am not on the bus. That means that if I plug into the DLC with a scope, I may not see what's happening on the bus. I see what's happening between the microprocessor and my scan tool. That is not the bus. You have to look at a wiring diagram. I mean, one of the most important things you're going to do here, you look at a wiring diagram. You have to see how it's wired. Where do the DLC wires go into? If you don't pay attention to this, you're doomed to fail. Doomed. You have to know where those wires go. Are these directly on the bus, or are these being filtered on the bus? What do we know now? We know that if we've got a Chrysler Jeep product, you are not on the bus. You are isolated. So the whole scan tool is totally isolated. So if you're going to go check termination resistance, did you check it? No! So you could still have a total problem with ringing or noise, and you're wrong. You're at the wrong place. This is a DLC, okay? Do you see how the scan tool, it's not connected? That's the bus. There's a big difference in those waveforms, isn't there? That means that I am isolated from the bus here. Now what I'm going to do is I'm going to plug my scan tool in, and now it looks like I've got a waveform. Well, if you don't understand this, you'd go check the DLC with your scan tool, and you would say, oh, I'm okay. Well, no, you're not okay. That means the scan tool to the bridge is okay. That does not mean that the bridge to the systems you want to check is okay. These are isolating from each other. You have to understand this. This is one of the most important things. I see guys in shop struggle with this. We have covered CAN C. CAN C is not fault tolerant. It will not take any problem on the high or low wire. You have a problem, you've lost communications. CAN B, this is called fault tolerant low speed. Now, is this really low speed? No, because there's still CAN A. This is what? Up to 125. 10 kilobits to 125 is CAN B. And this is a different standard. Now, everything changes in this standard. They want this system to be very fault tolerant, where I could have CAN high or CAN low, shorted to power, shorted to ground, shorted to each other, and I can still communicate. That's what this system is about. So it's very different. So basically, I'm going to use the same two-wire medium, right, which is a balanced scheme. When you use two wires, you're balancing the voltages, right? Because one's going up and one is going down. They're in opposing directions. The opposing current is going to ring out on the termination resistors, right? So basically, these are balanced, is what it's referred to. So this is the same way, and each wire carries a signal, and they're two different levels. So basically, this is very similar to what the other one is, except what? My speed and the voltages that they operate on. So this guy uses the same type of wire where I've got to twisted pair, but this is way different, isn't it? Look at the termination. Termination is done in each module. I don't have a 120 resistor to terminate myself out that's in the bus or in a module. Each module terminates itself out, and that's so if I short to power, I terminate the short across one resistance in one module so I can still control the current and I can still communicate. That's why it's done. This is one of the systems. We can see right here where we've got our twisted pair. Over here, we come in to the system. Note my termination resistors. Note you still have to have termination resistors, don't you? Because without any termination, we have ring echo. It's echo is the right word to refer to it. So here we have this system. Now this is going to go from 5 volts and 0 volts, and it's going to go to 3 volts to 2 volts. So my low is going to be at 0, and it's going to go up. It's going to go up, right, to 3, and my 5 is going to cross over low, and so I've got a really different waveform here. And this is fault tolerant CAN. This is the way that the circuit would have to be made in order for this to happen. We don't need to get into that. This is the waveform from it, right? Again, it's just opposing. If you see a waveform like this, you know that you're under 125 kilobits, that this is low-speed CAN. That's basically what that's telling you. Where do I use low-speed CAN? The DIM, right? Seats, all these other type of structures that we have. This isn't going to be used for engines, transmissions, ABS, steering position sensors. This is a much slower bus. So you remember how we said that on these slower buses that you don't expect a message back? That's because you would take up too much bandwidth, right? If you have to respond to every message that's coming in and you're expecting responses back and forth, you would tie all your bandwidth up. I've only got 125 kilobits on the thing. So if I tie my bandwidth up, I limit the amount of messages that I could carry. So they just eliminated that. They say we don't need to know if you talked or not. But you need to understand how all of a sudden you got a dead module without one code in it, how that happened. That's why. But on a high-speed bus, that would never happen because the other modules are expecting messages back, and they don't get them, so they code them. So CAN B single wire. This is LAN. So basically, I have a medium speed, 10 to 125, but I'm not carrying this on a 2-wire median. I'm carrying this on a single-wire median. And on the new systems, this CAN can go up to 500 kilobits. And I failed to mention that in CAN, there's a new CAN that's FD. It's flexible data, and it's used on the same bus. So you remember how we were talking about having an 11-bit identifier and a 29-bit identifier? Those two frames of data are being used on the same line. Those aren't different. Like, I don't have one system that does, 29 and one that does 11. The 11 and 29 are on the same system. They're both communicating, and they're both sending different messages at the same time. There's a new state, FD CAN. FD CAN can go to 2.5 meg, and it does that through a different way. To arbitrate and to have the bit selection for arbitration, you cannot go faster than 1 meg. So they arbitrate at 1 meg, and then there's a speed transition bit. Those reserve bits that I told you were there, there's a reserve O and a reserve 1. Those change states, and now I can actually put on FD CAN. FD CAN would be for programming. That's what they want it for. They want to be able to load very large amounts of data down through flexible data. Flexible data might even be run in regular systems to where I need more data transmissions. Right now, it's mainly used for programming the same way that this is. Once I arbitrate, I can speed the bus up, and I'm not looking to try to see if one is there compared to another when I'm not comparing. All I'm doing is banging the bus, right? I'm just sending bits out. So I can make the bits go way faster, and I can increase my data from having 8 bytes, 64 bits, and I can go up to 64 bytes now with flexible data. And that's something that can be run on the exact same system. I didn't have to change any of the physical layer. The computer's the same. This is all done in the software that this can all happen. So this is pretty cool stuff. Now I have really fast transmissions to where I don't bog things down, and it's just another way. This is another one that can produce up to 500 kilobits during programming only. This is a low speed, and during programming, we can go faster in certain conditions when we use bits correctly and we tell it we're doing something else. And the other thing that it slows back down, once we've set our data field, the payload of the frame, we send a transmission bit, and the transmission bit says to go slow down again. And it slows down because you have to have the acknowledgement. You cannot put a bit in or compare arbitration faster than 1 meg. Ain't going to happen, not with any reliability. So once we've put the message out on a high speed, we go to low speed again to put bits in. So arbitration and acknowledgement bits, those are changed, and there's a phase transition or a speed transition to use FD-CAN. So this guy, he's a single wire. It's the same carrier sense multi-access with collision resolution. That means all this other stuff we talked about, right? The median, those, remember how we looked at the different CAN standards? Well, that standard says I use 2 wires, I use 1. But CAN, it's just a language that says what I'm talking about here with all this data stuff, the way we're processing it. That's what's sort of the same. And then you look at the physical layers to figure out how many wires and all you got. But we're always dealing with a standard, just a sort of a generalized thing that this is how we're going to do this. And then you take it and you put your own flavor on it. So this is a single wire right here. If you see this, we have a Henry. Okay, so that's a choke. It's called a CAN choke. This is in all the systems. This can be in the systems. This is something to where we limit some of the noise and some of the problems, is what that's about. We don't need to get into that. This is basically what it's at. We go from 0 basically to 4.8, 5 volts, so it's a 0 to 5 volt signal. Each one of these is going to come up, and these are going to be frames of data, or packs. They are going to send a data load. Remember, in all these CAN frames, we have a lot of overhead to the frame to send not a whole lot of data, right? And that's just the way it's operating. And there's reasons for everything they've done. This is the system, and this is obviously a break, right? Where nothing's being transmitted. Again, you can see where we started. Notice how it's just one solid block almost. That's because everybody's on the bus trying to talk. So we got to wait to get our messages out, and over time, we're going to send a lot of messages. I want to make a note. Do you see this goes to 10 volts? That's the wake-up call in the system. These systems wake up and go to sleep. I didn't fail to tell you on Class C, the new chips. There's 2 chips that are available in Class C. Class C is what? 125 to 1 meg. Almost all Class Cs run at 500. It's a real common number that's used in cars for reality. Most of them are running 500 kilobits. I can have, before 2002, they had so many problems with these things waking up during the night and draining batteries that they changed the way the chip is made, and it has to have a wake-up now. So the new chips wake up, and there's a system for this to wake it up, and it wakes the chip up, and then it can come up. But erroneous voltages won't wake it up. On the older ones, just noise on the bus could wake them up, and then you drain batteries. And we've all looked for these type of battery drains. So you've got to realize that if you have noise on an older system, it can actually wake the system up, and it had nothing to do with the messaging system. The new ones have wake-up calls to where you don't have this problem. It was such a problem. This is the wake-up call on what? A single-wire CAN system. This is not dual wire. This is single. CAN A. This is less than 10 kilobits. We go from a high voltage of 12 volts, and we pull to ground. So this is going to be done a little bit differently. These are all real slow systems. Now, CAN A is really expensive. So CAN A is not what you're going to see on cars. You're going to see LIN. But basically, this is what CAN A is going to be. Notice my termination resistors, 2 9Ks that are off the wire, the main bus system. We always have termination. You've got to terminate. This is what you're going to probably have on your car. CAN A, I mean, when I was doing this class a while ago, it took me a while to find a CAN A car to even get a waveform because they're just not on cars. They're all too expensive. So what do we use? We use local interconnect network. Now, local interconnect network is really a different system. This is a slave master. So this guy, I've got a slave, and I got a master. The master has a quartz crystal in it, and the slaves use RC circuits for timing. So basically, this is a slave configuration. We pull down communication. This is a UART system. 12 volts to ground, no big deal here. Here it says master clock is a crystal and CAN is a crystal. What you got to realize, if you're a slave, you are not crystal. You are a RC circuit, a capacitor with a resistor. Now, those have no way to do anything really. In other words, the timing structure, I can't keep all my clocks in time. They're too crude. But I'm going at a really slow rate with this so I can play some games. Termination is 30K in the slave and 1K in a master. Here's the master, it's 1K. This is what's really different with the frame structure on this car. So basically, we have our brake. That brake isn't to do anything but tell everybody, wake up and get ready for a message. Now I'm going to pulse the sync, and I hit the sync a bunch of times. Every time I hit an edge, I do what? I resynchronize all the clocks so everybody's on the same clock. And the clocks are so crude because they're not quartz that I got to give a bunch of pulses to get everybody synced before I can give my ID and my data, my payload. Then we checksum it, because you always checksum all of these. All communication systems have a checksum. They all are going to check the message, and they're going to destroy the message, not use it or use it, depending on whether it was used correctly or not. And then I have interframe space. Interframe space means I'm idle before another message can be sent. These messages are all out of one processor, something like a SIM or a body control, and then he's controlling a very low-speed group, wipers, turn signals, trunk releases, whatever they choose to do with this. Most cars will have 3 buses. It's very common. The other thing is on the newer cars, you'll hardly ever see CAN B anymore. So you saw CAN B a lot, and now they've gone away from CAN B. So it's all high speed, except it might be 125 for my low speed, but they don't use that crossover waveform. You'll see a waveform like CAN C, where I'm at 2.5 volts, going up a volt and down a volt, so I go from 2.5 to 3.5 and from 2.5 to 1.5, opposing voltages, okay? So you'll see a wave like that. It's still high speed if it's 125, because that's what the standard says it is. I could run from 125 to 1 meg with this system. So that's what we're dealing with here. So you're going to not see lots of CAN Bs anymore. Everyone's gone to where they want more data rate. Most of the low-speed buses are running at 250 kilobits. High speed is running at 500. That's a really common new car now. Here's the LIN. So here we go. We can see this big break here. Again, that's for timing. Then we pulse, and then we send the data fields. Just a little bit different message. Vehicles have several different bus systems. I have a high speed, because we need it in some systems. And then we're going to have lower speeds, and then a real low speed. So we might have a CAN, 2 CAN systems, and then we have a LIN that's using really slow. Remember, everything that requires speed costs money. It's just like you guys that hot rod. I mean, I used to race, and I've wasted so much money. If I'd have been married, she'd killed me. You know, I wasted a lot of money on my race car. So you got to be smarter than that, right? You only want to use it where you got to use it. So we're not going to spend a bunch of money here. So this is just another way that we understand what we're working on. This is GM Class 2. Notice that we have a really similar format. We got CAN C, and that's yellow and green, and we've got red, and that's at 7 volts. Well, 7 volts means I'm what? Class 2. That's an older system, the different protocol. Similar, but different. And then we've got something that we would have CAN C and CAN B. But CAN B is what? Single wire interface. And we can send up to 125 kilobits on a single wire just fine. And single wire is cheaper. I don't have as much copper, I'm lighter, and I can do everything that I needed to do with CAN B. You can start to see why it's gone away, the 2-wire CAN B stuff. It's all gone to single wire, or it's gone to a high-speed system with dual wire if they need more speed. So this is a real common CAN system right here. What's needed for communications? Okay, when we do the scan tools, everybody would think that they wrote some standard, and this standard just works. You read this standard, and that's the way you build this thing, and you can talk to a car. Guys, that's the furthest thing that I've ever seen from the truth. They put a rule out there, and they said, guys, this is sort of what we want you to do. Would you sort of follow these guidelines? Sort of. In order to figure out how to talk to different modules, you've got to backwards engineer the timing bits, the handshakes, the time, everything. And it's got to be done on whatever kind of module you got, because they're all different. There's no one that used just the standard and said, this is the way we do it. They all put their own flavor on it. Their own flavor says that I got to backwards engineer it. I take this box right here, and only wires that I've got into that box, power, ground, and comm lines. That is it. To talk to these modules so I can backwards engineer them, I plug them into this box, I power them, and then we start banging it until we can communicate with it, and we figure out our timing sequences for the different cars. Here's a CAN module. What do I have? Powers, grounds, and comm wires. That's it. I want you to really realize this. If you have a communication problem, do all of those other wires have anything to do with your communication problem? Chances are they do not. You always got to factor in that if one of your 5-volt references is pulled to ground, you could pull the 5 volts down in the micro. If you remember back in the late 90s, early 2000s, you would pull down your 5-volt ref from a cam or a crank, and you couldn't talk to the car. Be really careful with that on newer cars. Drive-by-wire cars all have 2 5-volt systems in them. Because it's drive-by-wire, I need a safety-critical system, so I supply the APPS, the accelerated pedal position sensor, with a 5-volt regulator that is isolated for one of the circuits, and it's isolated totally from the other circuit. Grounds are isolated, signals are isolated. It's a safety-critical system. That's customer intent, driver intent. If the driver floors the car is going to make torque because the torque output was what was asked. And the task manager will carry that out. That means that I need 2 regulators. So I could short one out and I could still talk to it. So you need to think about that. So just a little bit different twist on it now. But basically you need what? Powers, grounds, and signal wires, and you can have communications. That's what you need to communicate on any of these modules. CAN bus waveforms that you need to know. Everyone here, we don't need to know a bunch of things. I hear all of this stuff where these people say, you got to have this scope, and you're going to look at this bitwise arbitration, and you're going to figure this out. They don't understand what they're talking about. To be on a CAN bus and to be able to interpret it, you have to have a CAN engine running. You know all the stuff I've been talking about? That has to be running. And you have to be checking your edges. Okay, so when we get an edge in CAN, we get the edge and they compare it against the prior time that the last bit happened. And then they equalize them, so if I get drift, I can still keep everybody talking. We're going to take this scope, and you're going to be able to look at this waveform to a microsecond or two with edges, and you're going to know what that message meant. I only wished I could. And I wished I could interpret the messages, because I would have a factory scan tool. I backwards engineer it. I'm telling you, it don't work like that. I only wish that I could go and I could get the data sets, and then I could set up what that data meant, and then everybody would have a factory tool. Everybody. Does everyone have factory tools? No, because that data is prioritized to the manufacturer that made it. And they're all unique, and it's unique coding to whatever manufacturer. And to try to break down any bitwise anything, don't waste your time. If you want to do that, I'll direct you to the right CAN digitizers. And it's a digitizer with an absolutely full CAN bus. It's what we use. And there's a couple of them we have. And it is not easy. And it is nothing we're going to do in a shop because it's a waste of your time. I want to show you how you fix cars, not how you engineer it. But you need some background to understand how I'm going to fix the car. So the waveforms that you need to know, that's one you need to know. That's accessory mode. If you get on a bus and you see that, 1.8 volts moving to 3.6. That's accessory. You're not powering the modules. That's what that's telling you. It's like when you put your key on and you're in accessory mode, you didn't light everything up. You're only part way there. The bus woke up, but he is still asleep, guys. Does that make sense to everyone? He's not ready for active communication. When you see this waveform, I'm going to show you how to use this waveform. It is one I see a lot during my diagnostics. This is active mode. I've come out of accessory mode. I've powered everybody, and everybody is awake. Now that everybody's awake, I'm going to have the 2.5 going to 3.5, going to 1.5, basically. Up a volt, down a volt, opposition. We're opposing why? To limit my noise transmission out of the wires. So basically, this guy is active mode. This is sleep mode. So I've told everybody to go to sleep. When you shut it off, you'll watch the messages and they start to diminish. The way sleep mode is on the CAN transceiver, there's a 5-volt pin and they take the 5 volts off of it. That tells the transceiver that I'm going to sleep, so he tries to dump all his messages and to finish up, and then you'll start to see it slow down. The reason that they're doing this is try to finalize the bus transmission so the next time it starts, everybody is ready, right? And you've got to give it enough time to get everybody adjusted, and that's what the sleep mode is. And notice that the difference here, I need to point out something. Notice how there's hardly any data in that? It does not look like accessory mode. Accessory mode, do you see how these have a lot of data in them? Do you see these data packs where I'm carrying data? If you look at sleep mode as I'm going to sleep, that's not the case. You hardly have any data. It's just saying that we're signing off and we're taking care of the bus. Bus ringing, you have lost your termination. It's echoing. That's what this is. So that's something to where you have what? More than one module connected and you've lost your termination resistance. This is acknowledgement. That means your wires are broken to the system. Does that make sense? Let's put our knowledge to work. We've got a 2006 VW Passat, no communications to the TCM. So we want to go get data. So we're going to get this. We've got the diagnostic interface bus. We've got a control module network. We've got refrigerant pressures, high, low. We've got a bunch of things. We've got more over here. No communication with the transmission module. That's the one I want to see. Okay? It says no transmission. When you do these, you're going to get into all of your system, high and low speed. Some of the clues are on the low speed because the bridge crossed it. I want to see who's got codes, who's not getting data. We're trying to make an assertion here on where my problem really is. And when these things start to fail, guys, you got codes for everybody. It isn't you don't got one code and, oh, this guy says he's bad. This doesn't work like that. I only wished it did. But we can already see that I can destroy another module's message and I never even got tagged. Be really aware of how this is going to work. And I can destroy messages all over the bus. I have codes from everybody. Now really, what's wrong? How do we find it? We're going to go in and we're going to look at low and high speed buses. We're going to get all the data. Make sure that you write your codes down or take frames, pictures on your scan tool. But make sure you know what they are. You better stop and you better look at a wiring diagram. And I am not just telling you this. You have to know how it's wired. Because how does that guy go in? Do you see how I'm going to come in here and I'm going to go into this guy? That's a data bus interface. What's that? A bridge. That does not mean that that DLC is connected to those wires on the other side of the bridge. You're going to have to prove that. You need to understand that. Because I'm at the DLC and I've got a bob or something and I've got a scope, that doesn't mean you're seeing what's happening. That means you're seeing a divided source. Here, I come up and we come out of my bridge and we come over and we're hardwired and we start splitting it. Do you see all these splits and do you see how that goes to the tranny? Okay, now I know how I'm wired. At least I have an idea, and I know I'm not directly on the bus, right? I did not come out of, I'm going to show you these, but I didn't come out of this into pin junctions where I'm directly on the bus. I went to some kind of an interface. And those interfaces are going to always change the way that we're going to communicate on the bus. Here's my CAN high speed at the DLC. Looks okay, right? Remember, we're not looking for bits. The bits are too complicated. You're not going to get anything. We need to know that the overall voltage levels, what are they doing? That's what I'm interested in. You know, if you want to decode it, don't you got another 5 modules on there that have been programmed to decode these messages? Don't they understand it better than we can? Use them. They're going to help you fix the car because they're coded in the same coding as what's happening on the bus to fail. If I can look at all the data and I can see what other module is telling me has failed, I'm going to do way better than trying to get a scope and do this. But I got to know what? That the basic voltage lines are okay. There I am at pin, I'm at the TCM now. What's wrong? The wires are broken. There's no acknowledgement. I mean, just to know a few waveforms makes such a difference to one when we're working on these. So now I know I've got broken wires. Now I want to show you something else. Do you see how I've got this K line? Be really careful here. So here's we got the no communication. This is just the acknowledgement that's missing. I want you to be really careful. You can have broken wires that do not communicate on the bus. There's no acknowledgement. Right? Right here. Do you see how I have no wire? He's asking, is anyone out there? Is anyone out there? Is anyone out there? There's no acknowledgement. This will go on indefinitely. It won't stop until he gets an acknowledgement bit put in there. Do you see how I got a K line? Wrong way. I can talk to that module on a K line. It depends on how your scan tool positions itself to go in to talk to it. So you'll go in and you'll see that you can talk to the module and you'll think he's okay, he's communicating. You're wrong. Your scan tool automatically picked another wire to go in and talk to it. You're not on the bus, you're on some other scan tool line. And this can happen on all kinds of stuff. I want you to be aware of it. So you could be looking, I just did a shop for, they've got a Duramax diesel. Well, they're using a different comm line. The main wire is down, so it's not communicating, and the codes are for communication. But he says, oh, no, look, it's communicating. That doesn't mean it's communicating. That means your scan tool is communicating. It doesn't mean the module on the bus is communicating. You've got to really think about this. You'll just get killed by this stuff. If you remember that, you'll be way ahead when you have one of these. I fixed the wires that went down by, they were broken right down by the transmission module. This car had been in a wreck. Someone had fixed the major portion where it got hit. Now I want to tell you, I do a lot of wrecked cars. When it takes a hit and you fix those and you still have a problem, go to the first to the second bend in the wiring harness. That's where the wires are broken. You know how when you pull on wires, sometimes they're so tight you can't even get them out to put an amp clamp on, and sometimes you get a yard out of it? When they're tight and it takes the hit and it jerks the wire, they just break the wires, clean breaks right at the turns. It's one of the, don't cut the whole wiring harness open. Just go up to the first or second turn. They're always broken there for me. It's where I expect to see them when they've been hit. And the shop, he didn't get it because he just fixed what he could see down where the actual damage occurred. He's not thinking about those wires are broken up on top, right? So we want to always be looking. Don't cut wiring harnesses open, guys. You'll do way more damage. We only cut wiring harnesses open if we've got somebody that put some too big a fuse or something like that. We melted things, or we've got multiple problems. But other than that, we don't cut wiring harnesses open. We wire around. 2008 Jeep Commander, communication problem. So we've lost the communication with the ECM, PCM. We've got implausible data from the PCM, ECM. We've lost communication to the steering angle. Do you see how all these are active? Always pay attention whether they're active or non-active. If they're active, we have the problem present. Implausible vehicle configuration. Am I worried about that? I don't care what VIN number's in this stupid car. It ain't why I'm working on it. Stay focused on what your problem is. Here we're looking at another module. So we've got CAN C off. We've got loss of communication with the ECM, PCM, incorrect config. I don't care about that. But we've lost communication with the anti-lock brake system, but it's not active right now. That means something happened in the past. We've got lost communication with the ECM, PCM. Again, this is the front gateway. This is the FICM. So basically, you start to see how we're going around to different modules trying to figure out who says who's failing. Do you see how a bunch of modules are failing? Well, which one is it? Oh, the ABS, or is it the TCM, or is it the PCM, or boy, there's a bunch. How are we going to figure it out? I want to go through all the data before I do anything. Whatever you do, don't go erase your codes till you fix it, because you didn't do anything, right? Always write down the codes or take pictures of them, right? But know what setting in what systems. Now, once I get an idea of what all is setting, do you see where I lost communication with the electronic gear, and that's active? But I've lost communication with the SCM. I've lost communications with the brake. I've lost communication with the PCM. Doesn't that make you think that somebody's wrong here? I've got somebody that's doing what? Getting bits in the way in the structure. Remember how we looked at this. Remember how it works. We go through arbitration. We set the RTR bit. Everything in front of that is not checked. After RTR, we check it with a cyclic redundancy check, and then we destroy the frame or we allow the frame to be. If we destroy the frame, every time we destroy a frame, that's 8 points. Then I've got to have 8 good transmissions to delete those 8 points. Do you start to see? So this is how we're going to get codes. We're going to set codes at somewhere 90 to 100 counts. So basically now we're going to look at this. How is it wired? So do you see right here, we come in and we've got this front module. So we come off of the DLC to a module. Guys, be careful now, right? We know that this isn't directly wired to the bus. We're going to have to do some checks to understand how this is going to operate. Okay, so now I come off of this guy, and this is the front control module, and I come over here, and do you see how I start wiring my main CAN bus off? Well, I've got a shifter assembly here, and I've got the engine control module, so I've got a bunch of things I can get to. This is a breakout box. If you don't got one, buy one. If you don't got this, you're wasting your time. And if you think you're back-pinning these things, you're going to ruin the connector so no one's scan tool will connect. You know, we don't back probe these. You don't stab them in the front. Just get someone's box. There's all kinds of breakout boxes. We plug into the DLC. Now this is going to give me attachment points for scopes. Do you notice what I said? Scopes. I didn't say a TTL meter. I didn't see anything like that. What I said is a scope. No meters. All that doesn't matter here. When you got a problem, you need one thing, and it's a scope on these communications. The other thing that's very helpful to have is a scan tool that you know can communicate with the bus. A factory scan tool is always good if you can get it. Because then if I can't communicate, I don't second guess, oh, wow, I wonder if that scan tool can talk to that module. And you just don't know. But if I've got a factory unit or equivalent, then I know I can. So if I can't talk to it, you know that the communications to that module are down. It's very important. Here I am at the DLC. Am I connected to the bus? So I'm isolated from the bus right now. Do you see this? So now I'm going to get the scan tool, and I'm going to plug the scan tool in, and I want to watch these waveforms. Here's the DLC with the scan tool connected. Now, that isn't going to matter, is it? Because I don't know if I'm on the bus. So I need to go get on the bus. In other words, this is where? The breakout box to the front control module, because that's what the wiring said. Now, that's my map. That looks okay, right? I don't see a problem with that. But I'm going to go over here and I'm going to look at the engine. And the reason I picked the ECM is because it's easy. Don't try to find the hardest thing there to find. Find the one that's easy. I popped the hood. That guy's right up on the firewall, right? So all I'm going to do is I'm going to get the wires. What? You already looked at a wiring diagram, didn't you? Don't you know what color it is? So it's white and blue, it's white and green, and they're twisted pair. So once you got the wiring colors and you find the two twisted pair, I can do this really quick, can't I? This stuff is easy. It's way easier than we make it out to be. What do you think? Does that look like a good waveform? Because it does not to me. This is at the PCM. Now, is there a big difference between the DLC and the PCM? Do you start to see if you're on the wrong end of the system, you're chasing your tail? You don't even know what you're doing. You've got to look at the wiring diagram. You have to understand that these systems are isolated, and they can be totally isolated or they can be connected. Yes? The question is, at the PCM, am I back probing? Yes. So basically, this waveform right here are from the CAN wires that would go to the powertrain control module. And here, to go back, these are what? These are from the box. That box there is giving me that waveform. That's between the scan tool and the interface. Then I'm going to have to go do something else, so I'm going to find the easiest box, usually an ABS module or an engine control module, because those are the easiest ones under the hood for me to find. I'm just trying to make sure I'm in a real system here, right? And here we can see I have two totally different waveforms. So here, what I'm interested in is this problem that I see here exhibited. So what's that? That's ringing, guys. That's ringing. I'm ringing. And the ringing is giving me all kinds of codes. Remember how all these modules are saying they're failing and they can't talk? Well, when I'm ringing, that ringing sets another bit, and that bit is what? It doesn't add up in the cyclic redundancy check, and it's going to flag it, and it's going to say that that is no good. We destroy the message, and then that counts 8 points against the guy who sent the message. Do you start to see how this is counting and how this is working? So now, I couldn't talk to the transmission, or I can't talk to this shifter. So I want to get on the shifter, and I want to look at the shifter, because it's another easy thing I can get to, right? I mean, I'm not going to take the dash apart to start with. I'm trying to get to the easiest things I can first. Where's my waveform? That's the shifter. Is that a good waveform? Those wires are not. One of them is broken, and one of them is made, and now it rings. Notice that this waveform that you see right up here, do you see that that's what's writing over here? It's the same signal, but you only have one wire that's doing it. The other wire is open. So now, I've got this figured out. So I'm going to take the same point of contact right here. I'm already in there, right, with my scope? And now I'm just going to run jumper wires, and I'm going to go jumper them into where? The engine control module. I'm in the wires out there already, right? Guys, I don't care about twisted wires. I'm just trying to diagnose the car. I'm a flat rate guy. I don't got time to rewire and twist wires. I'm at this shop for 20 minutes. Within 20 to 30 minutes, I have to know what's wrong with the car, because I've got to go and I've got to drive 10 miles, 15 miles. He's laughing because he's ridden with me. They was freaking out. These guys came out, and I don't think they were ready to follow me. I'm hauling ass, guys. This is a serious business. You got to make your shops. You got to make your stops. So basically, I'm going to bridge this. All I'm doing is just taking jumper wires, and I'm going to where I already am plugged in. I'm already plugged in at the engine controller, right? If I bridge these wires to that, and it's fixed, well, they're bridged. Isn't it fixed? Do you see that ringing anymore? The ringing is happening because you've broken a wire. That's what's happening here. And when the voltages are falling against dropping the voltage on the 120 ohm resistor, you're getting kicks from it, and it's not being able to be controlled. So basically, this is fixed. So now I need to bridge the shifter module to the dash. So basically, I'm going to take, and we're going to take a vise, and we're going to put 2 wires in a vise. I'm going to take a drill. I'm going to put the other ends of the wire, and I'm going to drill that tight. That's how you twist your wires. Super fast. I'm a mobile technician. I carry these wires with me. I have multiple colors of them, and I've got all kinds of them because I fix a lot of these systems. So in this case, I just have my twisted pair. They're with me. I've already made them, but this is the way you're going to make them in your shop. We want a good tight twist on them. So basically, we're going to take the twisted pair for the CAN system, and I'm going to put them from where? The shifter, and I'm going to solder them in, and I'm not going to cut the wires. Do not cut the wires. Just strip them, solder them, and then put liquid tape on them to seal them, and then run the wire up along the same harness that they're in, and put it under the dash to where you can find the other set of wires, and just twist. You're going to do the same thing to where I don't cut them. I'm going to just strip them back. I'm going to solder them, and then I'm going to put a good sealant on it, right? Liquid tape. I'm done. They couldn't fix this car for 2 weeks. I wired the car in less than 30 minutes, and I'm out of there. Do you start to see the difference with knowing a couple of waveforms? It makes a huge difference, guys. These aren't hard to do. 2008 Chevy Malibu, no start, no comm. This is my car. So here I've got no body, no radio, no EBCM, ECM, heat module, TCM. Everybody's dead, right? So we're going to go in and look for DTCs. Now some of this stuff I can talk to because I've got DTC counts, right? Here's my wiring. Once again, it's really important to look at this. The wires come up out of here into what? The ECM, there's a body control. And then I'm going to come down here with my high-speed wires, and these are my low-speed wires over here, right? So this is all low, and this is high. So to get these wires, they go up here and they come out here. That guy is part of that system now. They're not on the circuit directly. Here's a better view of what we've got. Here's where it goes down. Notice that when you get breakouts like this, it's saying, if I have this system over here, right, I'm going to come into there, and then I'm going to come and bridge out of there. Or I could come up if I don't have it, and I'm going to go into these wires. It just depends on what system it is. That's all the wiring is. It's not anything hard. Okay, so now I've got my breakout box here, and I've got my factory scan tool. What do you think? Do you think that the red and yellow look like a good CAN-C signal? We don't know very much, but I know that that's not going to work, right? So basically, the reason that I had codes from the low-speed system is because it's a different system, isn't it? Isn't that's LAN, GM LAN, which is CAN, right? Single wire application, J2719. So basically, this is just a different thing, right? That's all it is. But I can talk on that bus. I can't talk on the high-speed bus. Do you start to see why it's important to see who can't talk or what's not working? We just need to have a better understanding of what we're trying to fix here. This isn't going to communicate. Notice that we're pulled to ground, and both of these signals are pulled up. So this guy has got a problem. So here it is. I've just zoomed in on it. I need to start unplugging pieces now, because there's no other way to really do this. I start unplugging. What do I unplug? The easy things. Dude, I look for the easiest thing to start with, and then I start tearing dashes apart. But that's way down the road before I'm going to be there. So this guy's right up front, man. Okay, notice that he started to ring. I still have the problem, but now I've got part of my termination resistor missing because now he rang. Look back at this. Do you see how this guy, you don't see a bunch of pulses there, do you? You see one. Once I unplug that TCM, he's ringing and he's got the problem still. So is the TCM the problem? No, he's not the problem. because when I find the guy that's the problem, I'm going to recover that waveform. So now I'm going to go to the BCM. Did I fix the problem? BCM is the problem, right? That's where I'm having my problem. The BCM. So the BCM has failed, and the BCM, when he's failing, he's creating that. So now I unplug the BCM, and here I am. So I got a good waveform. I want to play a game. I want to show you guys something. I'm going to go back out on the TCM because that's where I am with these two wires. This is the two CAN, and I'm going to go into the car. And do you see how on my bridge, do you see how I've put them right into pin 6 and 14, CAN high and CAN low? Now I'm plugged into my scan tool. Can I talk to that car? No. Because you need a body control on that car, dude. Don't ever miscount what that body control does. When I'm telling you, you need to pay attention to if you've got a body control or you've got a bridge, I'm not joking. It will kill you to not know this stuff. So here I just wanted to make a point that I've got a signal there and I still am not there. And furthermore, what's that? No acknowledgement bit. Isn't it just repeating? Well, when I've unplugged it, I've got no acknowledgement. But the scan tool isn't going to put one in. You need one on the bus to do that. Do you start to see how this is working now? The BCM is bad. I installed the BCM and we reprogrammed the unit. The car's fixed. 2008, Mercury, Monterey. ABS track lights on, track lamp, brake lamp. ABS has some problem. This is the car. It's for a body shop. So here my track is on. So first thing I'm going to do, I take my scan tool. Again, this is a factory scanner. Not that you need that. You don't. It's just helpful because then I know whatever doesn't communicate, I'm not second guessing. I just know it can talk to it. And anytime I'm using just a generic scan tool, boy, you're just not sure. So how are we wired here? I've got my DLC and it goes into jumper pins. This is directly on the bus. When you get in a Ford and you plug into the DLC, you are on high and low bus wires. There is no interface. I'm not divided out of the system on this car. That makes a big difference for what I want to do now. Now that I'm looking at this, I see that I come off the DLC into my jumper pin. Notice how my jumper pins are breaking out. And then these are going to all my modules, right? I'm on the bus. So at the DLC, am I worried about it? No, I'm in the bus, and I know I'm in the bus now. So I don't have any kind of an interface here. So now I've got a good signal, don't I? Okay, so where do I got to go? The module I can't talk to. The module I can't talk to is the ABS, right? Track modules. Here's the ABS. Do you notice that that lock isn't provided? You don't have a connection to it. Whoever unplugged it they put it back up, but they didn't understand you got to lock it. These systems got to be locked so the connections come together. If I don't have the connector plugged into the unit, how on earth is it going to talk to anything? There's no way. So obviously I got codes, but it's so simple. It's as simple as this. What I'm trying to show you is its technique. It's following the same thing you're doing on every one of these. You're going to go to the module, okay? Sometimes it might be the module's bad. Sometimes it's not plugged in. Sometimes it's stable at 22. You need to clean the connector and put Stable-It on there, and that will fix your connection problem. If the connections are bad, you can get all kinds of noise in these systems. And I'm going to show you here shortly how much noise some of these can tolerate. Test the ABS system. It's all working. We have no problem. 2006, Chrysler. 300C, no start, no comm. Car's dead. Okay, so I put my factory tool on. Do you need a factory tool? No, but you need to know what's going on, right? All I care about is I got some data to make a decision. I always troubleshoot by symptom. Don't get all confused. Don't get all these DTCs and stuff and all that. What do you need to know to fix the car? Why am I working on it? Not how many parts the car's put on. Oh, the shop, they'll want to tell me, we've got this module and that one and this one and that. Does that matter? Well, whatever module they put on it, you still can't talk to it, so I could care less. I want to fix the car, not hang parts. Symptom diagnosis. Always, always stay with the symptom. You always fix the car. I can't talk to the PCM, the ABS, and the electronic shifter, but look, I can talk to the transmission. So when we go over here, do you see how this is can C, 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 and now I've got B? Well, all the can C's I cannot talk to except for what? The transmission I can talk to. And he says I've got 6 codes. But I can talk to the rest of the B, right? Which is slower protocol. Here we've lost communication with the anti-brake. We've lost communication with the PCM, the electric gear shift, HVAC. We got a bunch of different things here. How are we wired? It's so important to keep checking how you're wired. I've got the data link. The data link is going to come over to what? The front control module. Are you on the bus here? No, you're isolated from the bus. So you need actual wires in at the bus signals here, okay? So I'm going to go out, and what's the easiest module for me to get to? The PCM. Dude, that guy's right there. It is the ECM, actually. So I'm going to get into him. I'm going to find the 2 wires, right? I already looked at the wiring colors because I had the wiring diagram. They're twisted, aren't they? So don't I just got to find, how hard is this? This isn't hard. Don't make it hard. Every one of you can do this. You can do this. It's not hard. Now, what I want to do is I want to look at it with a scope. What's that waveform tell me? It's in accessory mode. That's accessory mode. It's 1.8 volt going to 3.5 volts. If it's got an accessory problem, what is that? It's a power or a ground. These guys didn't wake up. One woke up, didn't it? The tranny controller. So the tranny controller isn't the one I'm worried about. I'm wondering what's in common with the other modules. Start looking at a wiring diagram. Look at the powers and see if they're connected. See who all powers the same modules. You understand? Because this is a power problem. I didn't wake him up. That's accessory mode. You go back to the trunk, you see the spare tire right here? That 5 amp fuse right there powers all those computers that are off if you follow it back with a wiring diagram. That's the fuse. Put a fuse in, and hey, is that accessory mode anymore? Car's fixed. So we check the communications on the bus. Do you see all the can C's are cleared now? They're all working? It's just as simple as a power, just a blown fuse. Don't overcomplicate this, guys. You just don't need to. It's not that complicated. 2005, Ford, Focus, the dash lamps are on. When I say the dash lamps, the driver information panel, everything is lit. Car starts and runs, rest of it's working. Here's the dash system. We can see every light is on the dash, and I have no gauges, but the car's running, but I don't see any tack signals. So basically, well, there's not a tack there, so I misspoke. But basically, nothing's basically working here. I try to use my Ford tool. I cannot get into the system. It says no comm, so there's no communications. I can't talk to this car. He's dead. So I'm going to go to the DLC. Now, we looked at this on a Ford, and a Ford is directly wired to the bus, isn't it? So if I put a box on the DLC, I'm in the bus on a Ford. Does that make sense to everyone? So let's look at this waveform. What's that? It's ringing, echo. The wires are broken. So between where I am and somewhere else, I've got more than one module, and I've lost my termination resistance. That's what's happened here. As soon as I saw this, I know right away what's wrong. So the bus is ringing on this guy. So I'm going to go over to the PCM. He's right behind the glove box, right? And what I want to do is I want to get into the wires right here, into the PCM, and I'm going to bridge them over to the DLC. Notice I didn't wrap them. I'm not worried about I'm just proving my circuit, right? I just put 2 jumper wires and make sure that you don't cross them. Can high goes to can high, can low goes to can low. don't start bridging stuff. Pay attention. We're all professionals. That's an easy thing to do for us. Here I've bridged the system. Did I fix it? Yes, because it's not ringing. Why did it ring? Because I've lost the termination resistors with more than 2 modules on the bus. That's what happened here. So basically now I can get the data. I've got the car. I'm going to spin my wires. I actually had these in my car. Rick actually was with me, and Dave DeCourcy, bless his soul, and they drove around with me. This was one of the cars I fixed. Was I there longer than 15 minutes on this car? 20 minutes. This is easy stuff, guys. We overcomplicate it, I'm telling you. I'm going to bridge the wires from where? The PCM over to the DLC. And I'm not going to go start cutting wires open and harnesses because the shop ain't going to pay me for that. I'm just trying to do a quick repair. I've been doing this bridge stuff for a long time, and I don't have any cars coming back. Do it correctly. Don't cut wires, tee into them. Solder them and make sure that you seal it. Don't leave it unsealed. Whatever you do, you've got to seal it. Don't have any of your bridges longer than 3 feet. 3 feet's the longest bridge I'm ever putting in a car. I'm going to find somewhere I can bridge within 3 feet. You're allowed 3 feet off of stubs. That's part of the CAN standard. You're actually allowed 4. I cut it down 1. So you got, they say 4 feet from a stub. I'm saying 3 and I'll be safe. They say I can stub into that bus. It's part of the standard. Why can't you? Works for me, and it's worked for many years. 2008 Jeep Wrangler, no communication with the sway bar, and the shop has put a new sway bar module on here. This is my Wrangler. So here we go. We've got the CAN-C stuff. We're communicating. We can see we don't have codes until down here. We have a wireless control giving a code. Here we've got no communications for my sway bar assembly. And notice what it says, CAN-C. Okay, so here's I'm looking at the tip in. So this is the front module, the control module, where the bridge is what that is. So now I've got the codes, and I can see I've lost my sway bar module here, and it's active. But when I go look at the wiring diagram, does that say that's CAN-C? So now I'm really confused. The only wiring diagram I can find on this car, this is my sway bar. I've got a fuse, a ground, and what wire does that say it is? LIN, and that ain't high speed, is it? What's LIN? Less than 10 kilobits a second, and it's a single wire with what? A slave master. Here's the wiring diagram. We want to come down. We can see here that we've got my LIN system. Who controls the LIN bus? The instrument cluster. And he comes down. Can this be right? No, because it says that guy's on CAN-C. So the wiring diagram does not match the car. That's what I'm trying to show you. Now what am I going to do? I'm going to go look at the module he took off the car, because that's easy. Now I can do a count and a pin count so I can try to figure out which wires go in and what's what on it, right? Because the wiring diagram does not match the car. And we all have this, right? So you can't say, oh, how do I fix the car? You've got to figure out how you're going to figure out what the wiring is. Here's the only pin structure on that I could find. I've got power, ground, and it doesn't really tell me about what those wires are. But what do we know we've got to have communications? Power and ground. So this is the module he replaced. You can see the connectors down underneath here. I'm going to pop that connector, and I want to start to check my wires. I'm going to just start back probing until I can find some kind of a communication line. But what am I going to check first before I do all that? The easy stuff. Power and ground. Don't I have a power and ground schematic right there? Well, at least I know I can check that. And you know that the power and ground's got to be big, because that thing is bending that sway bar. And then you ain't bending no sway bar without having a lot of current on it, right? So I'm saying the power and ground on this dude, he's the big wires. The fuse is blown. That's all that's wrong with this car. It's just the fuse. So I didn't have to figure out the comm wires, but that doesn't matter. I could have done that, couldn't I? It's all a step. It's a procedure. Stay with the procedure. Don't get confused. Put a fuse in it, it fixed it. 2004 Volvo S60. The driving lights are on. The clock is running backwards. Do, 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 You know, I stepped in and I thought, Mr. Thompson, you have entered, you know. No, this is just a car. You don't enter any twilight zone. Okay, so basically, I wished I would have videoed it because it was so cool. The clock's just running backwards, and it was like, this is really a cool car, man. You know, the driving lights are on, and you're thinking, wow, that's pretty special. Haven't saw that one before. Here we've got the main complaint of the driving lights on, and I didn't film it, but that clock is running backwards. It is not going forward. So it's a very interesting car. Here's my fault codes. So we printed them out. This is a factory Volvo tool that I have. So basically, we've got the BCM nothing, CCM nothing. Now we've got an active code that's a CCM communication with the DIM. It's a driver information module, right? And that's active. The front relay lamp, he's got something, and it's found active. We have the power steering module, and the DTC is found not active, but it had one. So communication CCM, it's not active, not active, not active. The ECM is okay, the PDM, the RIM, no fault found. So basically now we've got an idea, right? Here's basically the same thing as my printout. Now, the shop that I'm doing this for is my buddy that owns a Volvo shop. And since he's got all the cool stuff, he's already got a breakout box on this thing when I get down there. But, dude, I don't get breakout boxes anywhere I go. But I'll take advantage of it when it's there. It's really cool, but you don't need it. It's really simple to figure them out. All I care about is what? We're looking at some wire. Here's my system. Do you see that guy right there? That guy is who I'm interested in. That's a module that's failing. And that module has a problem to where the CAN transceiver is failing. And that CAN transceiver, when it's failing, it's putting noise on that bus, and I'm failing all those other modules. Does everyone understand how this is working now? We understand how the system is in operation and how we count to get codes. That guy right there, that's the module I'm interested in. Now the problem is, it only happens every now and then. I can have this thing and I can let it, my scope, whenever you guys are doing this, I failed to tell you something very important. You do not want to trigger and you do not want to save the data over a period of time if you can avoid it. You want to have your scope and you want to have it, do you see how it says strip chart mode? And I don't want it fast. I want it slow so I can watch the packages run across the screen, so if one jumps up or down, I see it clearly and quickly. This isn't about looking at the bits. I'm not interested in getting the scope so fast I'm looking at these. Are the bits going to do me any good? It ain't going to fix the car I'm working on, guys. It might fix yours, but it doesn't fix mine. We make a 100 meg scope and I make a 50 meg scope. And I don't use either of them on this stuff. On this car, I had my 100 meg scope, and you know what it's got to do is it goes through data, and then it catches it, and then you sort of look through it. Well, every time for 20 minutes, I never, ever saw that fail right there, ever on my high-speed scope, because that's the missing data. Remember, I'm loading a buffer, and if I'm working really fast speeds, I overload the buffers really quickly. That means I drop the data. So when every time that was failing, that ain't when I got my data. And then I would catch another bunch, and then that wouldn't be when I got the data, because that's only happened once every couple of minutes or so. If I stream it, I'm just watching for the stream, and I'm watching for something to jump up, something to go low or high. Most of these that I see, they either go up like this or they go down, but the transceiver pulls both lines one direction. That is a module failing. And when you do your scope stuff, don't have it on triggers for this. You'll miss it. Have it streaming. Just have a bunch of data coming across where you can watch what's happening in live time. Then we're going to go try to figure out what module this is. That's a zoom in on it. So now I'm going to unplug the driver information, because isn't that an easy one to get to? Okay, we need to look at something, a wiring diagram once again. We're going to come up and we're going to go to what? The central module. So this is a central electric module. And then the module comes over and he feeds all these other wires. Do you see them all teed in? Now do you see how this comes up? And I want you to note that that goes into that dash. But do you see all these two wires that go up that feed the rest of that bus? So they go up and they feed the rest of this bus. Do you see how they start to split out up here? If I unplug that, I open the circuit to all these. If I open that circuit, what's going to happen? It rings. You made it ring. You unplugged it and you took the termination out because the termination is where? It's up here. And if you look back over here, do you see how these wires come in and I have these modules down here connected? And they come up over here, and if I unplug that, I have these to ring, but I took my termination apart from up here. Guys, you can't do this, okay? So you've got to bridge these. So before you unplug it, what did we always do first? We looked at a wiring diagram. Don't start unplugging stuff without knowing what you're unplugging. You don't even know how it's wired yet. So what I want to do is I can see that these go into the module and come out of the module. I want to bridge these wires like it's bridged inside that module. So I'm going to pull it apart and I'm going to put jumpers across them. Now when I unplug it, the only one I took out is the instrument cluster. And it doesn't ring because I didn't make it ring. Do you understand what we're doing here? Now I'm going to go look and I still got that stupid thing failing every minute or two. So did I fix it? No, so I got to go get another module and then I unplug another one. Always realize if you unplug something and it starts ringing, guys, you did that. You took the termination resistor out, now you got echo. Okay? So let's not do that. All you got to do is bridge them. And many of the modules, two wires go in, they come out the other connector. If you unplug the connector, wherever they went, that's open circuit now. You no longer have termination there. Does that make sense to everyone? What if the termination resistor is inside one of the other modules, the suspected module that I'm going to disconnect? I take a 120 ohm resistor from my decade box. I have them back there. You can look at them. I use decade boxes all the time. I've got two wires that come out. I tee into both the wires. I dial 120 ohms, and now I've got enough for a termination resistor. I put it in. If I suspect I'm missing one, I put it in and see if I can fix it. And sometimes that doesn't work because they need to be on the ends. They're placed in a certain position for ringing. The rim, isn't that an easy one to get to? Dude, I picked the easy stuff. Do you see all those modules that were up under the dash on this car? When I first started to work on it, I thought, oh my God, I'm only making 150 bucks on this car. If I got to start chasing those modules up under the dash, it's going to be more than 150, except it's my buddy, so it won't be. So basically, I unplug this guy back here, because this is an easy one. He's in the trunk. It's fixed. I no longer have that jump up. That jump, or the voltage levels that will be pulled up or down, that's the transceiver failing. We installed I'm so sorry, what?
Any water damage on that?
Any water damage? No, there's no water damage on this car. That isn't what failed. These modules, I don't get a lot of water, guys. I live in a desert. You get more water in a day than I get in a year. So it's a real difference. I live in the desert, and really we get like 12 inches a year. And that's a lot. I watch back here, and you get hit by some hurricane or something, and you get that in an hour. It's like, holy moly. If you could only share some of that water with us so our forest doesn't burn, right? So basically, this has got a rim. I put a new rim in. We reprogrammed it. The vehicle's fixed. 2006 Chevrolet Cobalt. No shift, no communication. We go to the transaxle, no comm. We look at this, and we're in the ECM now. I can't talk to the tranny, but the ECM has to talk to that tranny. Pick the module you're trying to talk to. Pick a module you know it has to talk to. So, I mean, if I got a tranny controller, I know he's got to be talking to the engine controller, right? So basically, I'm going to take this guy and I'm going to do the communication across this, and I'm going to pull it up, and he says he lost control with the tranny. So, okay, I'm lost control. The body control says I lost communication with the tranny. It says I lost communication with the steering module, but the difference is, notice that's a pass. That means it failed, but it's not failing right now. Here we've lost communication with the engine controller from the body control module. Again, start cross-checking modules. Never, ever look at the codes from one module and make any decision. Almost always I look at the whole low-speed bus and I look at the high-speed bus and I try to correlate. If the low-speed bus is missing data from the high-speed, that's telling me which side the problem's on, right? So play a game. Always look at all of them. I'm going to get into the wires. So here's the TCM. Does that look like a good waveform to you? Is that a good CAN-C? See, it's so simple. Every one of you now can do this. You can look at it and you know that that's not going to work. You can see that this guy is just not right. If we look up here, we've got, what, 4 volts. What's that supposed to be at? 2.5, not 4. Somebody's pulling the part where I'm not controlling it high. And as soon as we start to control it, that module can control it to what? 2.5. And when we let off, now it floats back up to where it's floating. So I need to unplug something. So here I'm going to unplug my transmission module. It's fixed. Tranny module's my problem, right? So now we just need to put a tranny module. What happens to these cars? Do you see that power post right there? They pull that guy up out of there because this is in a slide and it pulls up, and if you touch that, you blew that module instantly. The tranny shop did this. They blew the module when they pulled that up. They were pulling the tranny and they lifted that module up and it hit that power post on the battery. It's done popped right there. I see this happen quite a bit. This is another one I see a few times. So we put it in, we're going to reprogram it. I'm just going to use a J tool. This is a Drew Tech tool. Drew makes a great reprogrammer. In my opinion, it's the best. Here we've got no codes, the vehicle's fixed. 2002 BMW X5, no start. Here's my junk. Just joking. Engine controller, please wait. No communication. So I'm going to go to the tranny. No communication. I'm going to go to the immobilizer. I can talk to him. No fault. I want the ABS because he's the other guy on the high speed, right? I know he's on the high speed, so I want to pull the ABS here. So I'm going to pull the ABS. Now, notice what I've got in the ABS. Electric brake force, drive module running gear, transmission limp mode, running gear control module CAN bus. Do you start to see this? Who are all these guys referring to? The transmission module. He's not getting data from the transmission module is what this means. So there's no data present. So here's my box. I'm going to take these covers off. You can see these screws. I've got them back on to take the picture. I've already taken them off and done the work. So I pulled the DME out. And what do we need on a DME? What do you need? Power, ground, and comm wires. That's it. So if I chuck my power, ground, and comm wires, I got comm, I got some noise. Is that going to affect you? Not on a CAN bus, dude. These things are really tolerant of having some noise. Now, I'm not saying that that's great noise to have. I wouldn't say that, okay? But that noise is acceptable. That's not going to give me my problem. Power grounds are good. Do you see that hole? It rained the day before. The rain got in there and smoked both of those. If you ever see one of these covers that's broken, you better fix it. Because that cover is probably about $50, and those modules were $4,000. And then you got to set them up. So, I mean, it's all what you want to do, but if you're working on a customer's car and you see any kind of a leak like that, you need to fix it. The engine module and tranny, he ordered them. I went back and set them up for him. The car's fixed. 2006 Chrysler 300 check engine lamp, no comm. So when I start to look at this guy, okay, I want you to look at this. Do you see we've got what? B, 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 B. Where's any C's? So my front gateway, don't I see a gateway here for C? So I'm okay on C. Look at all the B's. And some of the B's aren't present, right? Like that's pretty crazy, but I have no C. Well, I'm here because the check engine lamp is on and this car runs. And the customer brought it in just for a check engine lamp. So let's take a look at what's wrong. Here's my factory tool. Hell, the whole bus is down. It says nobody's there. The car runs. Do you believe that? Always symptom diagnosis, guys. I'm not here for a no start. I'm here to fix some light that's on, right? Check engine lamp. That was why I'm hired. And they know they can't talk to the car. So here's my DLC. On a Chrysler, am I connected to the DLC? I want you to note, do you see how we have the DLC right here? This is the main bus. Do you see how this is being disrupted? Everyone see that? So that's a module that's bad, right? So I'm going to take my nifty Snap-on 2500. And do you see my nice little unit right here? Dude, look at that. I can talk to the bus directly. My fancy Chrysler tool will not talk to this car, and my MT2500 does. Why? When we backwards engineer a bus, I don't have any idea of what the proper wait times or bus banging I've got to do. We figure that out empirically until we can talk to the car. The same way Snap-on did. We're all in the same boat. When you get a factory tool, is what that thing knows is the exact wait times and the exact call-outs. So when it's on the exact wait time and call-out, there's latency. Remember, these bits have to come in at exact microseconds. If they're off, you don't communicate. Well, I've got something here that's just a shot in the dark because it's the same way I backwards engineer stuff. So I've got bigger wait times. So this is able to talk to it from the wait time. Does that make sense to everyone? Don't ever assume because you got a factory tool that that's the one to have. That's a mistake. Play around. See what one you got because everybody is going to play the game differently. I'm going to play it different than Snap-on because what we're trying to do, we're just trying to make it work. And however our times are and whatever we've learned, we apply to the next computer. Does that make sense to everyone? So here now I got my code. And what I've got a problem with is the transmission VSS. That's why the light's on. I fixed the wiring to this thing. The car's fixed. The light's out. I cleared the codes. Now, he don't want to fix the bus. I told him, dude, we ought to fix the bus. Don't you want to call your customer? I wanted another $150. That's the truth. Because it's easy to fix the bus. I can find the module pretty quick. And he goes, oh, no, we just want the light out. So, okay, I fixed his problem and it's fixed. Communication problem is there for the next guy that tries to get into this car. Do you start to see your problem? That ain't my problem. I turned the light out. I did my job. 1500 Ram. This is a 15, no dash, no start. This is my car. I'm going to turn the ignition. Nothing comes on. He's dead. So I want to look at a wiring diagram. And what I'm interested in on this diagram is I'm interested in the keyless ignition, and I'm going to look at him, and he's got a power and a ground, right? And look at what he's got, a K line. And this K line's going to come down, and this is going to go to the rear hub module. And that's a security line. And those two got to talk to wake up this bus, right? So if I turn the ignition switch and nothing starts, where am I going to start? Did the ignition have any kind of change? Did he send a message? Because that's what you got to have. Remember, guys, the guy that we're taught, these guys all have to send messages. And a message has to start. Well, what starts it? You turn the key. And if you turn the key, You said, wake up, because I'm here. I got a key in here. But he didn't wake up, did he? So there's something wrong. So the first place I'm going to go to, what? Isn't just common sense say, and then that easy to get to? Again, I'm into easy. I'm not going to some hard module to start this diagnostics. Don't you either. Don't make the mistake. So I want to get into here, and I can see the hub in the wiring diagram, but I'm not sure where that guy is yet. So I just dropped this bottom panel off real quick, back probed this ignition switch, and now we're going to look at it. I have a power and I have a ground. Do you see any change on that K line? How is it going to work? If I twist the key and I don't get a K line, is it going to work? He's not going to wake up, people. There's no way. That's my problem. What's wrong with the K line? Where did the K line go? It went to the rear hub. It's a security thing and behind the seat. Well, holy frickin' moly, I got more time in pulling the stupid seat out than fixing this car. And the seat was a pain to get out. It really was. It took me 15 minutes probably to get the seat out. But that's longer than it took me for the rest of the car. So here's my security. Here's the key. And I can get here and I don't have any signal. I come down here and here's my security K line right here. Got the seat out. So now we're going to check this. I'm going to check powers, grounds, and signals. Isn't that what you got to have? Power, ground, and signal. Okay, I have no K line. Now let's look at that. What is that signal right there? Anyone? What's that signal? It's accessory mode. That's accessory mode. Remember how I told you only need to know 5 waveforms? Stop worrying about bitwise resolution and all this stuff. That ain't the way you fix these cars. If you want to waste a lot of time, you just blow that scope picture up to every little bit and we see if we can fix it or not. I'm there to fix the car fast. I'm showing you how this really works. That is what? That's at 1.8 volts and it's going to 3.5. It's accessory. It does not have power. So all I got to do is check the power. Well, there's my power. And that power was at 5 volts, 3 volts, 2 volts. That was just where I got this picture. It's all over the place because I've got a voltage drop on the wire that goes back to this system. So here is the back hub. So now I need to check power and ground for the K line. Well, I don't got any power. That's my problem. So I'm going to look at the wiring diagram, and I'm going to be able to see that this guy sends power down from this fuse right here, and it splits right here. Now, I don't want to go find all that. I know that that fuse is good because don't I have power on the ignition switch? Wasn't I just in that ignition switch? So if I was just in that ignition switch, I'm already back probed, aren't I? Can't I just take a jumper wire from there to there? External? God, we overcomplicate it, guys. Just make it simple. Just bridge it. All I did is I'm going to bridge that wire right there because I'm in both places right now, right? Just string an outside wire. I'm not wrapping it inside the car. I've got 12 volts now. Look at the K line. Car starts and runs fine. The problem is in a voltage drop situation that goes from the key back to the hub module. This is not hard.
Let's remind them that this video is on the tablet.
This video is on your tablet, I am told. G, the master he is, has already put it there. So there's a whole video on how I fix this car. And in all honesty, I wasn't even over there to do this. I was over at this shop and I was dropping a car to get carbon. I really was. And this guy gives me a lot of cars. So he says, I got a problem. Can you look at this? So I found this really fast. And so I went and got a camera and I shot it just because I was there. But I was there to clean a car for him. He had a Beamer that was really dirty, and I cleaned a Beamer. And when I took it back, he said, can you take a look? And yeah, sure, I can take a look. So that's what this is. Now, when we look at this, do you notice that the CAN bus, we're 2.5 going up a volt, down a volt. Isn't that about where we expect? And this guy right here, this is my K line. Notice that big break. What's that tell you? This tells you that this doesn't have quartz crystals in it. It's waiting to time everything up, and then I'm hitting it with a bunch of pulses, and then I send my payload, my data. You start to see how if you just have a little knowledge on how these different buses work, you can tell what's going on just by the waveform. Dash is working. It's up and working. 2004 Volvo V70 XC. This is towed in twice. This is a crazy car. I went to this shop, and it was towed in. And they had already recovered the car. In other words, the whole car is dead. And they did a hard reset before I got there. So the car starts when I get there, right? So I look at it, and I'm not sure what's wrong with the car. So they sent it back out, and this is back again. This is another tow-in. But I told him, whatever you do, if this car comes back, do not do anything to the car till I look at this. Don't try to get it to run. Don't do anything. I want to see it. I need to understand what happened. So basically, here's my car. So here I'm in, and I'm trying to get in. Keys on. Everything is dead. Nothing comes up. Nothing works. The whole car is dead. He's all dead, right? I can't talk to him. This is a factory scanner I got. He's dead. He's not talking. Notice I don't have my buddy's breakout box. This is the way I really do it. Okay, you got to find the wires. I drop the SIM down. The SIM is right under the dash, right? Driver's side. I drop it down and I find my CAN lines right here, and I want to get into my CAN lines, high and low, right? I need both because we're transmitting data across this bus. To get this started, don't you have to have a security system? Now remember the Ford that we looked at that was ringing and the wires were broken on it? And it rang and I told you it started? I forgot to ask a question on that and I apologize. But I want you guys to think, why did it start if the bus is dead? That's because the anti-theft system sends a signal over a receive and a transmit directly to it. So the module is up on the steering column, and he directly talks to that PCM. He's not on the bus. So it starts and runs. Some of these cars, you've got to transmit the information from your security system from a low-speed bus to the high-speed bus, or it's not going to start. And you can have problems with the bridge not bridging that, and that's why it's not starting. So I want to make a point here. So basically, I want what? Low and high speed. I want to see who's coming up and who's not coming up. So now I've got this. Is that any kind of a waveform? No. Now I'll tell you, I'll give you an advantage that I know. Volvos, you're not on the bus until the SIM puts you there. So when you get a scan tool and you plug a scan tool into a Volvo, if you watch the bus, the whole bus rings for about a half a second, and then it's clear and you are on the bus directly. You know how when they says that you can set codes by plugging a scan tool into a Volvo? Dude, they're not joking. You rang the bus for a half a second. You set COM codes, you set them, because they say don't plug in a scan tool with the car running. They say plug it in with it off because they know it's going to ring. I know it rings because I look at all this on scopes, right? But I'm telling you, Volvo rings, and then you're on the bus. But until it rings, you're not on that bus, right? The SIM puts you on the bus. And now my wires are directly connected. It's like a Ford once I'm connected. And Volvo just does difference. You got to start to look at this stuff so you know what car you're dealing with. Here's the scan tool plugged in. I've got nothing. So if I can't get into the SIM so we can even request it to put me on the bus, well, then I'm not on the bus, right? But I'm on some of these wires that are not off of that. These, remember, I have the whole SIM down, right? If you look at the SIM, I'm in some of these wires that go out of the SIM, and I'm not part of the DLC. And they're all dead. Everybody's dead on this car. So now I'm going to have to do a reset because he's dead. So I take the two batteries and I put them together and I clear it. Now this is a hard reset, right? Now that I've done a hard reset, he works fine. But I want to show you something else. Do you say how I reset it and I drove this car for hours? Hours is an understatement. I drove this car for 8 hours to get this problem to reoccur. Here it is good when it's working. You can see that my power is functional up here. and I can see that this is my can. And notice what I'm doing. I'm just letting my scope run across and deep record. I'm not worried about this zoom stuff, guys. Who's failing? You'll see the voltages change. I don't need to see a bit change. I want to see that frame fail. And remember, you have to have multi-frames failing because you got to get to a count high enough to get kicked off the bus. And they do everything they can to not get you kicked off the bus, to make you passive, to make you not be able to talk for a period of time. They're trying to keep it on to where it can recover. Does that make sense? But we all know that now. Okay, so now here it is. We're good. Here we're failing. Notice one of the first things I see start to fail. The power's failing. But also, look at down here. Do you see how my CAN signals are failing? That power I'm in is sent out and controlled by the sim. And the reason, let me explain something else here. This waveform is because I'm taking 40 seconds of data. You can't take 40, I don't care who makes the scope. You got to match the scope frequency to the signal frequency. If I want to look at a really fast frequency like a CAN bus, I'm going to have to be really fast-paced if I want to look at bits. But I don't care about the bits right now. All I care about is package. I want to see the packages jump up and down, right? So if I put it on a longer time, am I worried about any kind of real sharp resolution? Your scope always matches the frequency. You know that because if you're looking at an O2 sensor and you've got the frequency at the fastest part of the waveform, all you see is this line popping up and down. There's no definition. I got to slow the scope frequency down to be within a certain margin of the signal I'm looking at so I can trace that waveform out and it's a meaningful waveform. If I'm faster than the signal or slower than the signal, there's no meaning to the signal. I alias. I don't have the data that I need to make decisions off of, right? The frequency of the scope has to match the signal. Well, if I want to match the signal, I'm going to make my scope go way faster. But if I make my scope go way faster, I can't drive it for frickin' 8 hours and watch it to start to see what's going to break down, to see these packets breaking down. Do you start to see what I'm trying to do here? Just be aware of what I'm trying to do. Here, now I've got a code set. And if you notice, we've got some faults. So we've got sim, faulty error, faulty error. Let's go here and we'll look at this. Do you see where this guy says the control module internal fault? This guy got thrown off the bus, guys. That's why the car died. Once you start to understand what I've gone over, you can understand this. He failed. They kept him passive. They kept him on the bus. The light was on, the check engine lamp. But if the car is going to die, wouldn't you expect the check engine lamps on? Does that tell you that this module's bad? No. The customer said the check engine lamp came on and then it died. Once you count to 256 failures and you hit that, that module is off of the bus. If it's the sim, you lose the high side, you lose the low side, and your car doesn't start. Do you see why I'm interested in the sim and I wanted to see the car when it first came up? Once you understand this stuff, it all makes sense. It's not that this car, oh, it died, oh my God, it died twice. No, the bus he got kicked off. And once he's kicked off, he cannot communicate until you do a hard reset. That's the truth. It's simpler now that we understand how this is working, some of the intricacies. I put a sim in this guy, we reprogrammed him, and we're done. You guys all know how to monitor this bus system now, don't you? Every one of you is going to go out and you're going to be able to look at some basic waveforms tomorrow in your bay. That's what I wanted to show you how this is done. I thank each and every one of you for coming. I know how hard it is for each one of you to come out here. I owned a shop for 28 years. I get older every year. I don't get smarter. My wife guarantees me that. But the one thing I can tell you guys, money comes and goes. All of it. Doesn't mean much. But your time, slips through your fingers like sand, and it will never, ever come back. It's gone. It is absolutely the most valuable thing that each and every one of you possess. Thank you for bringing such a valuable item and sharing it with me. Take
What an
care.
ass-kicking class. Bernie, again, you knocked it out of the park. Excellent job, Bernie. Excellent, excellent job. Unbelievable.